In the vast darkness between stars, something was moving toward us. For millions of years, it had been crossing the empty void, a messenger from another world, carrying secrets we had never imagined. Most people think our solar system is like a walled garden, protected and isolated from the chaos beyond. Or we picture it as our own private cosmic neighborhood, with the sun's family of planets spinning safely in their eternal dance. But what if I told you that we're not alone? What if I told you that visitors from other star systems pass through our cosmic backyard more often than we ever realized? On October 19th, 2017, astronomers discovered something that changed everything we thought we knew about our place in the universe. An object unlike anything ever seen before, tumbling, accelerating, and behaving in ways that defied explanation. It appeared from nowhere, stayed just long enough to mystify us completely, and then vanished back into the darkness. And Arksue in Dupain Zeblap, Gisimo. The question that haunted scientists wasn't just what this object was, but how it could have appeared so suddenly, as if materializing from empty space itself. Join me as we unravel the mystery of ʻOumuamua, the most enigmatic visitor our solar system has ever received. Before we dive into this cosmic mystery, I'm curious, where are you watching from right now? And what's your local time? Are you discovering this mystery during your morning coffee, or perhaps pondering the cosmos late at night? Drop your location and time in the comments below. I love seeing how this story reaches people across our planet at different moments of their day. The night sky above Maui's Haleakala Observatory was crystal clear on October 19, 2017. Dr. Robert Werrick, a soft-spoken astronomer from the University of Hawaii, was doing what he had done hundreds of times before, scanning telescope images for potentially hazardous asteroids that might threaten Earth. It was supposed to be routine work, the kind of methodical sky surveying that rarely makes headlines. But as Werrick analyzed the images captured by the Panoramic Survey Telescope and Rapid Response System, known as PANSTARS, something caught his attention. There, moving against the background of distant stars, was a faint point of light. At first glance, it looked like just another space rock tumbling through our solar system. But something about its motion was wrong. Most asteroids follow predictable paths, orbiting the sun in elliptical trajectories that astronomers can map and predict. This object, however, was moving too fast and in the wrong direction. As Werrick traced its path backward through previous images, a stunning realization began to dawn on him. The mathematics were telling him something extraordinary. This object wasn't orbiting the sun at all. It was passing through our solar system like a cosmic highway, coming from somewhere else entirely. Within hours, Werrick had alerted the international astronomical community. Telescopes around the world swiveled toward this mysterious visitor, and with each new observation, the impossible became undeniable. The object's trajectory showed it approaching from the direction of the constellation Lyra, following a path that could only mean one thing. It had come from interstellar space. For the first time in human history, we had detected a visitor from another star system. The discovery sent shockwaves through the scientific community. Dr. Alan Fitzsimmons from Queen's University Belfast captured the moment perfectly. We have discovered the first interstellar asteroid. It's really weird. But weird was just the beginning. As more observations poured in, this cosmic traveler would prove to be far stranger than anyone could have imagined. The object was given a name befitting its unprecedented nature, ʻOumuamua, Hawaiian word, meaning messenger from afar arriving first. Taverian Sal, it was a name that would soon become synonymous with mystery, controversy, and the humbling realization that our solar system is far more connected to the galaxy than we had ever understood. But here's what made the discovery even more remarkable. ʻOumuamua hadn't just appeared from nowhere in a cosmic sense, it had literally appeared from nowhere in an observational sense. Despite our advanced survey systems constantly scanning the sky, no one had seen it coming until it was already here, already past its closest approach to the sun, already beginning its journey back into the darkness. How does a 400-meter-long object simply materialize in our solar system without warning? The answer lies in the vast scales of interstellar space and the limitations of even our most sophisticated detection systems. ʻOumuamua had been approaching us for thousands of years, but against the backdrop of infinite space, it remained invisible until it was practically on our doorstep. As telescopes around the world focused on this interstellar visitor, the first detailed observations began to paint a picture of an object unlike anything in our solar system. The initial excitement of discovery quickly gave way to scientific bewilderment, as each new measurement revealed characteristics that challenged our understanding of how celestial bodies should behave. The most immediately striking feature was ʻOumuamua's brightness variations. As it tumbled through space, the object displayed dramatic changes in luminosity, brightening and dimming in a regular pattern every 7.3 hours. This wasn't unusual in itself. Many asteroids rotate and show brightness variations as different faces catch and reflect sunlight. But the magnitude of ʻOumuamua's brightness changes was extraordinary, suggesting an object with an extremely elongated shape. Dr. Karen Meach, from the University of Hawaii's Institute for Astronomy, led the international team studying the object. Her calculations suggested that ʻOumuamua was at least 5 to 10 times longer than it was wide, more like a cosmic cigar than the roughly spherical shapes typical of asteroids and comets. "This is really a mystery," Meach explained to her colleagues. "We've never seen anything like it in our solar system." The spectral analysis, essentially the cosmic fingerprint revealed by studying how the object reflected different wavelengths of light, was equally puzzling. Most asteroids show clear signatures of specific minerals and compounds, telling stories of their formation in the early solar system. ʻOumuamua's spectrum was remarkably featureless, appearing almost neutral in color with a slight reddish tint. This suggested a surface that had been altered by millions of years of exposure to cosmic radiation during its journey through interstellar space. Even more intriguing was what the spectrum didn't show. Unlike comets, which typically display clear signs of water, ice, and organic compounds, ʻOumuamua showed no evidence of these materials. It wasn't behaving like a comet either. As it approached the sun, it showed no signs of outgassing, no development of the characteristic tail that forms when solar heat vaporizes a comet's icy surface. The object's trajectory provided another clue that something fundamental was different. When astronomers calculated its path with extreme precision, they found that ʻOumuamua was moving on what's called a hyperbolic orbit. Unlike the elliptical paths of planets and typical asteroids, this was an open-ended trajectory, a cosmic slingshot that would carry the object through our solar system once and then fling it back into interstellar space forever. But perhaps the most unsettling aspect of those early observations was the object's size, or rather, how difficult it was to determine. Based on its brightness and distance, astronomers estimated ʻOumuamua to be roughly 400 meters long, about 4 football fields end to end. But this calculation depended on assumptions about how reflective its surface was, and with such an unusual object, those assumptions might be completely wrong. The more scientists studied ʻOumuamua, the more questions emerged. Where had it come from? How long had it been traveling through space? What was it made of? And most puzzling of all, why did it seem so different from everything else we knew about small bodies in space? About small bodies in space. These questions would soon become even more pressing as ʻOumuamua prepared to reveal its most mysterious characteristic, yet one that would divide the scientific community and launch a debate that continues to this day. The discovery of ʻOumuamua presented astronomers with an unprecedented challenge. How do you study the first visitor from another star system when it's already leaving and will never return? Unlike asteroids or comets that orbit the sun and can be observed repeatedly over months or years, ʻOumuamua was on a one-way journey back to interstellar space. Every passing day made it fainter, more distant, and harder to study. Dr. Davide Farnocchia, from NASA's Jet Propulsion Laboratory, captured the urgency perfectly. We had to act fast. This was a once-in-a-lifetime opportunity, and we were watching it slip away hour by hour. The international astronomical community mobilized with unprecedented speed and coordination. Telescopes from Hawaii to Chile, from space-based observatories to ground-based giants, all turned toward this cosmic visitor. The European Southern Observatory's Very Large Telescope in Chile's Atacama Desert, became one of the primary instruments for detailed observations. Its four 8.2-meter mirrors, working in perfect synchronization, gathered every photon of light reflected from ʻOumuamua's surface. Even with this tremendous light-gathering power, the object appeared as nothing more than a faint point of light, a cosmic needle in the haystack of space. What made the situation even more challenging was ʻOumuamua's rapid motion. The object was traveling at about 26 kilometers per second relative to the Sun, fast enough to cross the United States in less than 5 minutes. What made the situation even more challenging was ʻOumuamua's rapid motion. This breakneck speed meant that astronomers had to constantly adjust their telescope pointings, tracking the object as it raced across the sky like a cosmic bullet. The window for detailed study was closing rapidly. By late November 2017, just 5 weeks after its discovery, ʻOumuamua had already traveled beyond the orbit of Mars and was becoming too faint for most telescopes to detect. The object's brightness was dropping exponentially as it moved away from both the Sun and Earth, following the unforgiving mathematics of the inverse square law. NASA's Spitzer Space Telescope, sensitive to infrared radiation, made valiant attempts to detect heat emanating from the object. These observations could have revealed crucial information about ʻOumuamua's size, composition, and temperature. But even Spitzer, one of the most sensitive infrared telescopes ever built, couldn't detect any signal from the increasingly distant visitor. The Hubble Space Telescope, humanity's premier observatory, was pressed into service for what would become some of the most precise astrometric measurements ever attempted. Hubble's exquisite stability and resolution allowed astronomers to track ʻOumuamua's position with incredible accuracy, creating a detailed map of its trajectory through the solar system. These measurements would later prove crucial in revealing the object's most mysterious characteristic. As December 2017 approached, the scientific community faced a sobering reality. ʻOumuamua was becoming too faint to observe with existing technology. The object that had captivated the world's attention was about to disappear forever, carrying its secrets back into the darkness between stars. The final observations came from the Gemini Observatory in Hawaii, where astronomers squeezed every last photon of data from the fading visitor. By January 2018, ʻOumuamua had passed the orbit of Jupiter and was essentially beyond the reach of ground-based telescopes. The brief window of opportunity had closed. But even as the object itself vanished from view, the data collected during those frantic weeks would continue to yield surprises. Hidden within the precise measurements of ʻOumuamua's position and motion was evidence of behavior that would challenge our understanding of physics and launch 1,000 scientific papers. The irony wasn't lost on astronomers. After waiting millennia for our first interstellar visitor, we had been given less than 2 months to study it. Robert Werrick, the discoverer, reflected on the experience. It was like being introduced to a fascinating stranger at a party, only to watch them walk away forever after the briefest conversation. Yet in those precious few weeks, ʻOumuamua had already begun to transform our understanding of the universe. The data collected during the race against time would reveal secrets that continue to puzzle scientists today, and perhaps most importantly, the discovery had opened our eyes to a new reality. We are not alone in the cosmic dark. Visitors from other star systems pass through our neighborhood, and now we know how to find them. As the initial excitement of discovering our first interstellar visitor began to settle, scientists faced the challenging task of determining what ʻOumuamua actually looked like. The object was far too small and distant to photograph directly. Even through our most powerful telescopes, it appeared as nothing more than a faint point of light. Yet hidden within that simple dot of luminosity was a geometric puzzle that would reshape our understanding of celestial objects. The key to unlocking ʻOumuamua's shape lay in its light curve. The pattern of brightness changes as it rotated through space, like a cosmic lighthouse. The object's irregular form caused it to reflect different amounts of sunlight, depending on which face was pointed toward Earth. Dr. Karen Meach's team at the University of Hawaii analyzed these brightness variations with meticulous precision, watching as ʻOumuamua dimmed and brightened in a rhythmic 7.3-hour cycle. What they discovered was unprecedented in the annals of astronomy. The dramatic brightness variations a factor of 10, between the dimmest and brightest phases, suggested an object with an aspect ratio unlike anything previously observed in our solar system. While typical asteroids might be twice as long as they are wide, ʻOumuamua appeared to be at least 5 times longer than it was wide, and possibly as much as 10 times longer. To put this in perspective, imagine a cosmic cigar roughly 400 meters long, but only 40 meters wide, a needle-like object tumbling end over end through the void. No known asteroid or comet in our solar system exhibits such an extreme elongation. The closest comparison might be some of the more unusual near-Earth asteroids, but even these pale in comparison to ʻOumuamua's radical proportions. The implications of this discovery were staggering. How does nature create such an elongated object? In our solar system, the processes that form asteroids and comets typically produce relatively compact, roughly spherical bodies. Collisions might create irregular shapes, but the extreme elongation of ʻOumuamua suggested formation processes completely alien to our experience. Dr. Alan Fitzsimmons from Queen's University Belfast, who led some of the early spectroscopic observations, was struck by the object's uniqueness. In over 30 years of studying asteroids and comets, I've never encountered anything remotely like this. It's as if nature decided to show us something completely new. The elongated shape also raised questions about the object's structural integrity. How could something so thin and elongated hold together during its millions of years' journey through interstellar space? The gravitational forces trying to pull it apart would be significant, especially for such an unusual geometry. Yet ʻOumuamua appeared to be tumbling in a stable, predictable manner, suggesting it was indeed a solid, coherent object. Some scientists began to wonder if they were looking at a fragment of a much larger body, perhaps a piece broken off from a larger asteroid or comet by some cosmic collision. This could explain both the unusual shape and the object's journey through interstellar space. If ʻOumuamua were debris from a collision in another star system, it might have been ejected with enough velocity to escape its parent star's gravitational pull. The shape mystery deepened when astronomers realized that their calculations might be conservative. The brightness variations they observed represented the minimum elongation ratio. If ʻOumuamua were oriented with its long axis perpendicular to Earth's line of sight, it could be even more elongated than their estimates suggested. Disjected, some models proposed an object that might be 15 or even 20 times longer than it was wide. This revelation forced astronomers to confront an uncomfortable truth. Despite decades of studying small bodies in our solar system, we had never encountered anything that could have prepared us for ʻOumuamua's bizarre geometry. The object was challenging our fundamental assumptions about how celestial bodies form and evolve. While ʻOumuamua's elongated shape was startling enough, the way it moved through space added another layer of mystery to this cosmic enigma. The object wasn't simply spinning like a football thrown in a perfect spiral. It was tumbling in a complex, chaotic motion that spoke to a violent and mysterious past. Dr. Wes Fraser from Queen's University Belfast led the effort to understand ʻOumuamua's rotation state. Using data from multiple telescopes, his team discovered that the object was in what astronomers call a tumbling or complex rotation state. Unlike the stable rotation of planets or the predictable spin of most asteroids, ʻOumuamua's somersaulting through space with 2 distinct rotational axes. The primary rotation period was 7.3 hours. This was the rhythm of brightness changes that had first revealed the object's elongated shape. But hidden within this primary cycle were subtle variations that suggested a secondary rotation with a much longer period, possibly weeks or months. It was as if ʻOumuamua was simultaneously spinning like a top and wobbling like a badly thrown football. This complex rotation pattern is typically the signature of an object that has experienced significant trauma when asteroids collide or when comets are torn apart by gravitational forces. The resulting fragments often exhibit exactly this type of chaotic tumbling. The rotation state was like a fossil record written in motion, preserving evidence of some catastrophic event in ʻOumuamua's past. But when had this trauma occurred? Or the timescales involved were mind-boggling. If ʻOumuamua had indeed traveled from another star system, its journey might have taken millions of years. During such an epic voyage, the object would have experienced minimal external forces that could affect its rotation. This suggested that whatever event had set ʻOumuamua tumbling had occurred, either very recently or very long ago, possibly during its ejection from its parent star system. The tumbling motion also provided crucial insights into the object's physical properties. Dr. Sylvia Protorpa from the University of Maryland used sophisticated modeling to show that ʻOumuamua's rotation state was consistent with a relatively dense rocky object rather than a loose pile of debris. A fragmented or weakly bound object would have been torn apart by the complex rotational forces over such a long journey. Perhaps most intriguingly, the tumbling motion affected how astronomers interpreted the object's shape. The complex rotation meant that different aspects of ʻOumuamua were presented to Earth at different times, creating an intricate pattern of brightness variations. Some researchers suggested that the object might be even more unusually shaped than initially thought, perhaps not just elongated, but also flattened, like a cosmic pancake, or even resembling a flat disk. Dr. Sergei Mashenko from McMaster University proposed that ʻOumuamua might be extremely thin and flat rather than cigar-shaped. His models suggested that the observed brightness variations could be explained by a disk-like object with a thickness-to-width ratio of about 1:10. This would make ʻOumuamua not just unusually elongated, but possibly one of the flattest objects ever observed in space. The implications of such a shape were staggering. How does nature create a cosmic pancake? No known formation process in our solar system could produce such a geometry. This led some scientists to consider more exotic possibilities. Perhaps ʻOumuamua was a fragment of a much larger layered object, or the remnant of some process completely unknown to terrestrial physics. The tumbling motion also had practical implications for the ongoing observations. As ʻOumuamua rotated, its changing orientation affected how much sunlight it reflected toward Earth. This made it challenging to accurately determine the object's size and composition, as these calculations depended on knowing precisely how the object was oriented relative to Earth and the Sun. Dr. Marco Micheli, from the European Space Agency's Space Situational Awareness Program, noted the observational challenges. It's like trying to measure a spinning coin from across a football field while wearing sunglasses. The tumbling motion makes everything more complicated. But it also tells us something important about this object's history. The rotation riddle became even more complex when astronomers realized that ʻOumuamua's tumbling motion might be evolving over time. The subtle gravitational influences of the Sun and planets, combined with possible outgassing effects, could gradually alter the object's rotation state. This meant that the tumbling pattern they observed might be different from what it had been during its interstellar journey. As ʻOumuamua continued its journey away from the Sun, its complex rotation carried it through space like a cosmic acrobat. Each tumble and spin a reminder of the violent forces that had shaped its mysterious past. The rotation riddle would prove to be just one piece of a much larger puzzle, one that would challenge our understanding of physics itself. Determining the true size of ʻOumuamua presented astronomers with one of the most challenging inverse problems in modern astronomy. The object was too distant and too small to photograph directly, yet understanding its dimensions was crucial for unraveling its mysteries. The solution required a combination of sophisticated physics, creative modeling, and a healthy dose of scientific detective work. The primary tool for estimating ʻOumuamua's size was photometry, the precise measurement of how much light the object reflected. This technique, used successfully on countless asteroids and comets, relies on a fundamental relationship. The amount of light an object reflects depends on both its size and its surface reflectivity, known as albedo. Unfortunately, astronomers had no way of knowing ʻOumuamua's albedo in advance, making the size calculation a complex puzzle. Dr. Davide Farnokia from NASA's Jet Propulsion Laboratory explained the challenge. It's like trying to determine the size of a distant light bulb when you don't know how bright the bulb is. We can measure the light we receive, but without knowing the object's reflectivity, we can only estimate its size within a range of possibilities. The initial calculations, based on ʻOumuamua's brightness and distance, suggested an object roughly 400 meters long. But this estimate came with enormous uncertainty. If the object had a very dark surface, like some carbonaceous asteroids with albedos of just 3 to 5%, it would need to be much larger to reflect the observed amount of light. Conversely, if it had a bright, icy surface with an albedo of 50% or more, it could be significantly smaller. The problem was compounded by ʻOumuamua's unusual elongated shape. Traditional size estimates assume roughly spherical objects, but the extreme aspect ratio meant that astronomers had to develop new mathematical models. Karen Meach's team created sophisticated three-dimensional models that took into account the object's rotation, orientation, changing distance from both Earth and the Sun. These models revealed that ʻOumuamua's size estimates were highly sensitive to its assumed shape. If the object were indeed cigar-shaped, with dimensions of roughly 400 by 40 meters, it would have a surface area much larger than a spherical object of the same mass. This increased surface area would affect both the light reflection calculations and the object's thermal properties. The thermal modeling became particularly important when NASA's Spitzer space telescope attempted to detect infrared radiation from ʻOumuamua. All objects in space emit thermal radiation based on their temperature, which depends on their size, composition, and distance from the Sun. Spitzer's failure to detect any infrared signal from ʻOumuamua provided crucial constraints on the object's size and thermal properties. Dr. Davide Trilling, from Northern Arizona University, who led the Spitzer observations, used the non-detection to establish upper and lower bounds on ʻOumuamua's size. The lack of detectable thermal emission suggested either a smaller object than initially estimated, or one with unusual thermal properties. Combined with the visible light observations, this narrowed the size estimate to between 100 and 1,000 meters in length. The size mystery deepened when astronomers considered the object's mass. Unlike size, which could be estimated from reflected light, ʻOumuamua's determination required observing ʻOumuamura's gravitational effects on other objects or detecting changes in its motion. Neither approach was feasible, given the object's small size and brief visit to our solar system. Without knowing the mass, astronomers couldn't calculate ʻOumuamua's density, a crucial parameter for understanding its composition and internal structure. Was it a solid rock, a loosely bound rubble pile, or something else entirely? The density would provide vital clues about the object's origin and the processes that had shaped it. Dr. Alan Harris, from the German Aerospace Center, attempted to address this problem by comparing ʻOumuamua's brightness variations with those of known asteroids. His analysis suggested that the object's rotation and brightness patterns were consistent with a coherent, solid body rather than a loose collection of debris. This implied a density similar to rocky asteroids, roughly 2-3 grams per cubic centimeter. But even this seemingly straightforward analysis was complicated by ʻOumuamua's unique properties. The object's extreme elongation meant that its brightness variations were more dramatic than those of typical asteroids. This made it difficult to apply standard techniques developed for more conventional celestial bodies. The size uncertainty had profound implications for understanding ʻOumuamua's origin and journey. A smaller object would be more easily ejected from its parent star system, but would also be more susceptible to destruction during its interstellar voyage. A larger object would be more robust, but would require more energetic processes to achieve the escape velocity needed for interstellar travel. Dr. Corinne Baylor-Jones, from the Max Planck Institute for Astronomy, used statistical models to explore the relationship between size and origin. His work suggested that objects like ʻOumuamua might be relatively common in interstellar space, but our ability to detect them depends critically on their size and reflectivity. The discovery of ʻOumuamua might represent just the tip of an iceberg of interstellar objects passing through our solar system. The size puzzle also affected calculations of ʻOumuamua's structural integrity. An object with the extreme elongation suggested by the brightness variations would experience significant internal stresses, especially during its tumbling rotation. Dr. Yun Zhang from the University of Nice used finite element modeling to show that such an object would need to be composed of relatively strong material to maintain its shape over millions of years. Perhaps most frustratingly, the size uncertainty meant that many of ʻOumuamua's most intriguing properties remained ambiguous. The object's surface composition, thermal evolution, and even its basic classification as a rocky asteroid or icy comet all depended on parameters that couldn't be determined with certainty. As ʻOumuamua faded from view, astronomers were left with a sobering realization. Despite deploying some of the most sophisticated telescopes and analysis techniques available, they had been unable to definitively determine even the basic physical properties of humanity's first confirmed interstellar visitor. The object had guarded its secrets well, leaving behind a legacy of questions that would fuel scientific debate for years to come. In the world of astronomy, spectroscopy is like having a cosmic fingerprint scanner. When sunlight bounces off an asteroid or comet, it carries with it the chemical signatures of the minerals and compounds on the object's surface. These signatures appear as distinct patterns of absorption and emission lines in the spectrum, a technique so powerful that astronomers can determine the composition of objects millions of kilometers away. But when scientists turned their spectroscopic instruments toward ʻOumuamua, they encountered something unprecedented: virtual silence. Dr. Alan Fitzsimmons, from Queen's University Belfast, led the international spectroscopic campaign to decode ʻOumuamua's composition. Using some of the world's most sophisticated spectrographs, including the X-shooter instrument on the Very Large Telescope in Chile, his team captured detailed measurements of the light reflected from the mysterious visitor. What they found, or rather what they didn't find, would add another layer to the growing mystery. ʻOumuamua's spectrum was remarkably featureless, unlike the rich absorption patterns typically seen in asteroids, which reveal the presence of silicate minerals, iron compounds, and organic materials. ʻOumuamua showed an almost neutral reflectance spectrum, with only a subtle reddish tint. This lack of distinctive spectral features was itself a clue, but one that pointed toward multiple possible explanations. The reddish coloration was particularly intriguing. In our solar system, objects develop reddish surfaces through a process called space weathering, the gradual alteration of surface materials by cosmic rays, solar wind, and micrometeorite impacts over millions of years. The fact that ʻOumuamua appeared reddish suggested it had indeed spent an enormous amount of time in space, consistent with its interstellar origin. But the degree of reddening was puzzling. Dr. Fitzsimmons compared ʻOumuamua's color to that of objects in our outer solar system, particularly the populations of small bodies beyond Neptune. The color was similar to some Kuiper Belt objects and certain types of asteroids, but not identical to any known class of solar system body. It was as if ʻOumuamua existed in a spectral category all its own. The featureless spectrum also raised questions about the object's surface composition. Most asteroids show clear signatures of specific minerals, olivine, pyroxene, feldspar, that tell stories about their formation in the early solar system. There's Praisdexi and Siphi, Area Soin Siphi. Comets typically display evidence of water ice, carbon compounds, and organic materials. ʻOumuamua showed none of these characteristic features, presenting instead a smooth, unremarkable spectrum that revealed little about its internal composition. Dr. Sylvia Protopa, from the University of Maryland, attempted to extract more information from the subtle features that were present. Her analysis suggested that ʻOumuamua's surface might be covered with a layer of organic material that had been darkened and reddened by cosmic ray exposure over millions of years. This organic coating, or space-tan as some scientists called it, could be masking the underlying composition of the object. The implications were significant. If ʻOumuamua's surface was indeed covered with processed organic materials, it might indicate that the object had formed in a region rich in carbon compounds, perhaps in the outer regions of another star system, where temperatures were low enough for organic materials to condense. This would make ʻOumuamua not just a visitor from another star system, but a potential carrier of complex chemistry from an alien world. However, the organic coating hypothesis faced challenges. For such a coating to survive the interstellar journey, it would need to be relatively stable and bound to the underlying surface. The vacuum of space, cosmic radiation, and the thermal cycling experienced during the object's approach to our Sun would all tend to erode or alter such materials. Yet, ʻOumuamua's spectrum showed no clear signs of ongoing surface changes. Some scientists proposed alternative explanations for the spectral silence. Dr. ʻOumuamua suggested that ʻOumuamua might be composed of materials that were simply unfamiliar to terrestrial astronomy. If the object had formed in a star system with different conditions than our own, perhaps around a different type of star, or in a region with unusual chemistry, it might contain minerals or compounds that had never been observed before. The lack of spectral features also meant that astronomers couldn't determine whether ʻOumuamua was more similar to an asteroid or a comet. In our solar system, these two types of objects have distinctly different compositions and origins. Asteroids are typically rocky and metallic, formed in the warm inner regions of the solar system. Comets are usually icy and rich in organic compounds, formed in the cold outer regions. ʻOumuamua's spectrum provided no clear indication of which category it belonged to. This ambiguity would prove to be more than just an academic curiosity. The distinction between asteroid and comet would become crucial when astronomers discovered that ʻOumuamua was behaving in ways that defied easy classification. The spectral silence had left them without one of their most important tools for understanding what this mysterious visitor truly was. As ʻOumuamua approached the Sun during its brief visit to our solar system, astronomers expected to witness one of the most fundamental behaviors in cometary science, the formation of a tail. For centuries, humans have watched comets develop their spectacular tails as they near the Sun, creating some of the most beautiful and dramatic sights in the night sky. But ʻOumuamua, despite coming within 0.25 astronomical units of our star, stubbornly refused to play by the rules. Dr. Karen Meacher's team at the University of Hawaii monitored ʻOumuamua throughout its solar approach, using sensitive cameras and spectrographs to detect any signs of outgassing, the process by which solar heat vaporizes ices on a comet's surface, creating the characteristic tail and coma. They found nothing. No tail, no coma, no detectable gas or dust emission whatsoever. This absence was deeply puzzling. When comets from our outer solar system approach the Sun, they typically begin showing activity at distances of 3-5 astronomical units, well beyond the orbit of Mars. By the time they reach ʻOumuamua's closest approach distance, they should be displaying spectacular tails millions of kilometers long. The lack of any visible activity suggested that ʻOumuamua either contained no volatile materials or had lost them long ago. The implications were significant for understanding the object's origin and composition. In our solar system, objects formed in the cold outer regions typically retain large amounts of water, ice, carbon dioxide, and other volatile compounds. The absence of such materials in ʻOumuamua suggested either that it had formed in a warmer environment than typical comets, or that it had been processed by some mechanism that removed its volatile components. Dr. Olivier Hanot from the European Southern Observatory noted the unprecedented nature of this observation. We've never seen a comet-like object from the outer solar system that shows absolutely no activity when heated by the Sun. It's as if ʻOumuamua had been freeze-dried by its journey through space. Some scientists propose that ʻOumuamua might have been depleted of volatiles during its ejection from its parent star system. If the object had originated close to another star, or had been heated during a violent ejection event, its surface layers might have been stripped of ice and other volatile materials. This would leave behind a rocky or metallic core that would show no activity when heated by our Sun. Alternative explanations focused on the object's long interstellar journey over millions of years in the vacuum of space. Cosmic rays and solar wind from nearby stars could gradually erode surface materials and drive off volatile compounds. Dr. Aurélie Gilbert-Lepoutre from the University of Lyon created models showing how such processes could completely desiccate an object like ʻOumuamua over cosmic timescales. But the missing tail mystery deepened when astronomers realized but the lack of outgassing created a paradox. While ʻOumuamua showed no visible signs of comet-like activity, its behavior in other ways suggested it might indeed be releasing small amounts of gas, just not enough to be detected directly. This invisible outgassing would soon prove to be the key to understanding one of ʻOumuamua's most perplexing characteristics. The absence of a tail also affected how astronomers classified the object. Without clear evidence of either rocky asteroid-like composition or icy comet-like behavior, ʻOumuamua existed in a taxonomic limbo. The International Astronomical Union ultimately classified it as both the first interstellar asteroid 1I ʻOumuamua and the first interstellar comet ʻOumuamua and the first interstellar comet KEIS 2017 U1, reflecting the scientific community's uncertainty about its true nature. Dr. Robert Werrick, who had discovered the object, reflected on the classification challenge. We found something that doesn't fit into our existing categories. It's not quite an asteroid, not quite a comet, but something entirely new. The missing tail was our first hint that we were dealing with an object unlike anything in our solar system. The mystery of the missing tail would prove to be intimately connected to ʻOumuamua's most controversial characteristic, its inexplicable acceleration away from the sun. The lack of visible outgassing had hidden a subtle but crucial process that would challenge our understanding of physics and launch one of the most heated debates in modern astronomy. One of the most fundamental questions about ʻOumuamua remained maddeningly elusive. What was this mysterious object actually made of? The answer lay in determining its density, the mass packed into each cubic meter of material. But without a way to directly measure ʻOumuamua's mass, astronomers found themselves engaged in a complex detective story that would reveal just how little we understood about our first interstellar visitor. The density question was crucial because it would determine whether ʻOumuamua was a solid, coherent object like a rocky asteroid or something more exotic, perhaps a loosely bound rubble pile, a hollow shell, or even something composed of materials unknown to terrestrial science. Each possibility would tell a different story about the object's origin, composition, and journey through space. Dr. Alan Harris, from the German Aerospace Center, approached the problem by analyzing ʻOumuamua's rotation and brightness variations. His calculations suggested that the object's tumbling motion was consistent with a solid body rather than a loose collection of debris. A rubble pile or weakly bound object would likely have been torn apart by the complex rotational forces during its millions of years' journey through interstellar space. But determining the actual density value proved far more challenging. The calculation required knowing both the object's volume and its mass. While astronomers could estimate the volume from the size and shape measurements, the mass remained completely unknown. Unlike planets or moons, which reveal their masses through gravitational effects on other objects, ʻOumuamua was too small and too brief a visitor to produce measurable gravitational influences. Dr. Corinne Baylor-Jones, from the Max Planck Institute for Astronomy, took a statistical approach to the problem. He reasoned that if ʻOumuamua were a typical rocky asteroid, its density should be similar to known asteroid densities, roughly 2 to 3 grams per cubic centimeter. This would make it comparable to terrestrial rocks like granite or basalt. Using this assumption, he calculated that ʻOumuamua would have a mass of approximately 100 million tons. But this assumption was immediately challenged by other scientists. Dr. Sergei Mashenko from McMaster University argued that ʻOumuamua's extreme elongation and unusual behavior might indicate a much lower density. His models suggested that the object could be as light as 0.1 grams per cubic centimeter, less dense than cork, and comparable to aerogel, one of the lightest solid materials known. The low-density hypothesis had profound implications. If ʻOumuamua were indeed so light, it might be a hollow shell or a highly porous object filled with empty space. Such a structure could explain some of the object's unusual properties, including its extreme elongation and its mysterious acceleration away from the sun. Dr. Zdenek Sekanina, from the Jet Propulsion Laboratory, proposed that ʻOumuamua might be a fragment of a larger object that had been hollowed out by some process, perhaps sublimation of internal ices during its interstellar journey. This would leave behind a thin shell of refractory material that could maintain its shape while having a very low overall density. The density debate was further complicated by the object's unknown composition. If ʻOumuamua were made of materials common in our solar system, silicate rocks, iron, or water ice, its density would fall within predictable ranges. This density would fall within predictable ranges. But if it contained exotic materials or had been processed by conditions unknown in our solar system, its density could be completely different from anything previously encountered. Some scientists began to consider even more exotic possibilities. Dr. Abraham Loeb from Harvard University suggested that ʻOumuamua's properties might be consistent with an artificial object, perhaps a light sail or probe created by another civilization. Such objects would necessarily have very low densities to achieve the large surface area to mass ratios required for efficient propulsion by radiation pressure. The density question became even more pressing when astronomers discovered that ʻOumuamua was accelerating away from the Sun in ways that couldn't be explained by gravity alone. This acceleration required some form of propulsion, and the amount of force needed depended critically on the object's mass and density. A lightweight object would require less force to accelerate, while a dense object would need more. Dr. Marco Micheli from the European Space Agency attempted to use the acceleration measurements to constrain ʻOumuamua's density. His analysis suggested that the object's mass must be low enough to allow the observed acceleration to be produced by plausible physical processes. This pointed toward a density on the lower end of the estimated range, perhaps 0.5 to 1.5 grams per cubic centimeter. The implications of a low-density ʻOumuamua were staggering. It would suggest that interstellar objects might be fundamentally different from the solid, dense bodies we're familiar with in our solar system. They might be more like cosmic snowflakes, fragile, porous structures that somehow maintain their integrity during journeys lasting millions of years. As ʻOumuamua disappeared into the darkness beyond our solar system, it left behind a fundamental question about the nature of matter in space. The density debates continued to rage among scientists, with each new theoretical model offering different insights into what this mysterious visitor might have been. The answer would prove crucial for understanding not just ʻOumuamua itself, but the entire population of interstellar objects that might be passing through our cosmic neighborhood. In the annals of astronomy, few discoveries have generated as much scientific controversy as the moment when researchers realized that ʻOumuamua was accelerating away from the Sun, not slowing down as expected, not following the predictable gravitational dance that governs all celestial mechanics, but actually speeding up in defiance of everything we thought we knew about how objects move through space. Dr. Marco Micheli from the European Space Agency was the first to notice something amiss in the precision tracking data. As part of the international effort to map ʻOumuamua's trajectory, Micheli had been using observations from the Hubble Space Telescope to create an ultra-precise map of the object's path through the solar system. These measurements, accurate to within a few kilometers across distances of hundreds of millions of kilometers, were designed to predict exactly where ʻOumuamua would be at any given time. But when Micheli compared his predictions with new observations, he found a discrepancy that sent shockwaves through the astronomical community. ʻOumuamua was roughly 40,000 kilometers away from where it should have been based on gravitational calculations alone. This might sound like a small error given the vast scales involved, but in the precise world of celestial mechanics, it was equivalent to losing track of a baseball and finding it in the next county. The discrepancy wasn't random. It showed a clear pattern. ʻOumuamua was systematically deviating from its predicted gravitational trajectory in a way that suggested it was being pushed away from the Sun by some unknown force. The acceleration was small, roughly 1/10,000th of Earth's gravity, but it was persistent and undeniable. Dr. Davide Farnocchia from NASA's Jet Propulsion Laboratory, who had been tracking the object since its discovery, was initially skeptical. My first reaction was to check our calculations, he recalled. Objects don't just accelerate away from the sun without a reason. There had to be an error somewhere. But as more observations confirmed the anomaly, the scientific community was forced to confront an uncomfortable reality. ʻOumuamua was behaving in ways that violated our understanding of how objects move through space. The acceleration appeared to be non-gravitational, meaning it couldn't be explained by the gravitational pull of the sun, planets, or any other known mass in the solar system. This was unprecedented for an object showing no signs of cometary activity. When comets accelerate away from the sun, it's because solar heating vaporizes ices on their surfaces, creating jets of gas that act like tiny rocket engines. But ʻOumuamua showed no visible signs of outgassing, no tail, no coma, no detectable emissions of any kind. The magnitude of the acceleration was precisely what made it so puzzling. It was too large to be explained by radiation pressure, the gentle push of sunlight itself, acting on such a small object. Radiation pressure can indeed accelerate objects in space, but the force is incredibly weak. For a ʻOumuamua to experience the observed acceleration from radiation pressure alone, it would need to be extraordinarily lightweight and have an enormous surface area relative to its mass. Dr. Avi Loeb from Harvard University was among the first to suggest that the acceleration might indicate something truly extraordinary about ʻOumuamua's nature. The acceleration is telling us that this object is not what we initially thought it was, he argued. Line Jude, it's either made of materials we don't understand, or it's structured in ways that violate our assumptions about natural objects. The timing of the acceleration was also significant. The non-gravitational force appeared to be strongest when ʻOumuamua was closest to the sun, then gradually weakened as the object moved away. This pattern was consistent with some form of solar heating effect, but the absence of visible outgassing made it difficult to explain through conventional comet-like processes. This was the ʻOumuamua infra. ʻOumuamua. Some scientists proposed that ʻOumuamua might be outgassing materials that were simply too difficult to detect with existing instruments. Perhaps the object was releasing hydrogen gas, which would be nearly impossible to observe directly, but could still provide enough thrust to produce the observed acceleration. Or perhaps it was venting some other transparent gas that left no visible trace. But even these explanations faced challenges. For invisible outgassing to produce the observed acceleration, ʻOumuamua would need to be losing mass at a rate that seemed implausibly high for such a small object. The outgassing would need to be precisely directed and sustained over weeks or months, a level of activity that seemed inconsistent with the object's inert appearance. Dr. Zdeněk Sikanina from JPL proposed that ʻOumuamua might be a fragment of a larger comet that had been torn apart by tidal forces or some other catastrophic event. Such a fragment might retain enough volatile materials to produce outgassing, but in amounts too small to create a visible tail. This could explain both the acceleration and the absence of typical comet-like activity. The acceleration anomaly also raised questions about the object's internal structure. If ʻOumuamua were a solid, dense object, it would be much harder to accelerate than a lightweight, porous one. The fact that it was accelerating at all suggested that it might be far less massive than initially estimated, or that it had an internal structure that amplified the effects of whatever force was acting on it. Perhaps most troubling for astronomers was the realization that the acceleration was changing over time. As ʻOumuamua moved away from the sun, the non-gravitational force was gradually weakening, but not in a simple, predictable way. The complex pattern of acceleration changes suggested that multiple processes might be at work simultaneously, or that the object itself was evolving as it traveled through space. The discovery of ʻOumuamua's acceleration transformed it from an interesting astronomical curiosity into one of the most controversial objects ever observed. The acceleration couldn't be explained by conventional physics without making assumptions about the object's composition or structure that seemed to violate everything we knew about how celestial bodies form and behave. As news of the acceleration anomaly spread through the scientific community, it triggered a flood of theoretical papers attempting to explain the impossible. Some proposed exotic materials, others suggested unusual structures, and a few even dared to consider the possibility that ʻOumuamua might not be a natural object at all. The mystery of the impossible push had opened a Pandora's box of scientific speculation that would challenge our understanding of the universe itself. The discovery of ʻOumuamua's mysterious acceleration triggered one of the most intense scientific detective investigations in modern astronomy. Faced with an object that seemed to defy the fundamental laws of celestial mechanics, researchers around the world launched a coordinated effort to find a rational explanation for the impossible. What followed was a masterclass in scientific methodology, as astronomers systematically eliminated possibilities while searching for the truth hidden within the data. Dr. Davide Farnokia from NASA's Jet Propulsion Laboratory led one of the most comprehensive investigations into conventional explanations for the acceleration. His team began by examining every known force that could possibly affect an object moving through the solar system. They considered gravitational perturbations from planets, moons, and even large asteroids. They analyzed the effects of solar radiation pressure, the solar wind, and the subtle influence of the sun's magnetic field. None of these forces could account for the observed acceleration. The team then turned their attention to more exotic gravitational effects. Could ʻOumuamua be responding to gravitational waves rippling through space-time? Could it be influenced by dark matter or some other mysterious component of the universe? The calculations showed that while these effects exist, they are far too weak to explain the object's behavior over the timescales involved. Dr. Alan Harris from the German Aerospace Center focused on the possibility that ʻOumuamua's unusual shape might be amplifying known forces in unexpected ways. His models explored how an extremely elongated object might interact with solar radiation pressure differently than a spherical body. The calculations showed that while shape could indeed affect how radiation pressure acts on an object, the effect was still orders of magnitude too small to explain the observed acceleration. Meanwhile, Dr. Olivier Hanault from the European Southern Observatory investigated whether ʻOumuamua might be losing mass through some previously undetected process. His team analyzed the object's brightness variations and spectral properties, looking for any signs of material being ejected from its surface. They found no evidence of mass loss, but the lack of detection didn't rule out the possibility entirely. Subtle outgassing processes might be occurring below the threshold of observational detection. The investigation took a new direction when Dr. Yun Zhang from the University of Nice proposed that ʻOumuamua might be experiencing thermal effects that had never been observed before. As the object rotated and tumbled through space, different parts of its surface would be heated and cooled by the sun in complex patterns. This thermal cycling could potentially create pressure differences that might contribute to the acceleration, though the calculation suggested the effect would be minimal. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy approached the problem from a statistical perspective. He analyzed the orbital characteristics of known comets and asteroids, looking for any precedent for the type of acceleration ʻOumuamua was displaying. His research revealed that while some comets do show non-gravitational accelerations, they are always accompanied by visible outgassing activity. ʻOumuamua's combination of acceleration without visible activity was genuinely unprecedented. The detective work became even more complex when researchers realized that the acceleration wasn't constant. Marco Micheli's continued analysis of the Hubble data revealed that the non-gravitational force was changing in strength over time, following a pattern that roughly corresponded to ʻOumuamua's distance from the Sun. This suggested that whatever was causing the acceleration was somehow linked to solar heating, even though no thermal effects were visible. Some scientists began to explore the possibility that ʻOumuamua might be composed of materials that were completely unknown to terrestrial science. Sergei Mashchenko from McMaster University proposed that the object might contain exotic forms of matter that could interact with solar radiation in ways not predicted by conventional physics. While intriguing, these theories were difficult to test without direct samples from the object. The investigation also considered the possibility that ʻOumuamua might be a fragment of a much larger object that had been destroyed by some catastrophic event. Zdenek Sekanina from JPL developed models showing how tidal forces from a massive planet or star could tear apart a comet-like body, leaving behind fragments that might retain enough volatile materials to produce subtle outgassing. This could explain both the acceleration and the absence of visible comet-like activity. As the scientific detective work continued, it became clear that conventional explanations were struggling to account for all of ʻOumuamua's unusual properties simultaneously. The object's extreme elongation, its lack of visible outgassing, its mysterious acceleration, and its unusual spectral properties seemed to point towards something genuinely unprecedented in our experience of solar system objects. Dr. Robert Werrick, who had discovered the object, reflected on the challenge. We're trying to solve a puzzle where we only have a few pieces, and some of them don't seem to fit together using the rules we know. It's forcing us to question our assumptions about how objects behave in space. The systematic elimination of conventional explanations was gradually leading the scientific community toward an uncomfortable conclusion. ʻOumuamua might represent something genuinely new in our understanding of the universe. The detective work had revealed that this mysterious visitor was not just unusual, it was challenging the very foundations of our knowledge about how objects move through space. The failure of conventional physics to explain ʻOumuamua's acceleration forced the scientific community to confront a disturbing possibility. Either our understanding of celestial mechanics was fundamentally incomplete, or this mysterious visitor represented something entirely outside our experience of natural objects. The implications reached far beyond a single anomalous space rock, touching on the very foundations of how we understand the universe. Dr. Avi Loeb from Harvard University was among the first to articulate the profound nature of the challenge. When we encounter something that doesn't fit our existing models, he explained, we have two choices: modify our theories to accommodate the new data, or consider that we might be observing something that operates under different rules entirely. The acceleration anomaly was pushing astronomy toward this uncomfortable crossroads. The most immediate implication was for our understanding of small body dynamics in the solar system. For over a century, astronomers had successfully predicted the motion of asteroids and comets using Newton's laws of gravitation, combined with well-understood non-gravitational forces like rocket-like outgassing. ʻOumuamua's behavior suggested that there might be classes of objects that don't follow these established patterns, forcing scientists to expand their theoretical framework. Dr. Darrell Seligman from the University of Chicago explored the possibility that ʻOumuamua's acceleration might be caused by hydrogen outgassing, a process that had never been observed before, because hydrogen gas is extremely difficult to detect directly. His calculations showed that if ʻOumuamua were composed largely of hydrogen ice, it could produce enough thrust through sublimation to explain the observed acceleration while remaining essentially invisible to our instruments. But the hydrogen hypothesis raised its own troubling questions. How could an object made primarily of hydrogen ice survive the extreme conditions of interstellar space? Hydrogen has the lowest boiling point of any element, and even the minimal heat sources in the interstellar medium should have caused such an object to evaporate long ago. The survival of a hydrogen iceberg for millions of years seemed to violate our understanding of thermodynamics. The implications extended beyond physics into the realm of astrobiology and a search for extraterrestrial intelligence. If natural processes couldn't adequately explain ʻOumuamua's properties, some scientists began to consider whether the object might be artificial in origin. This possibility, while controversial, couldn't be dismissed entirely, given the object's unprecedented characteristics. Dr. Abraham Loeb took this line of reasoning furthest, proposing that ʻOumuamua might be a piece of technology created by another civilization. His calculations showed that an artificial light sail, a thin reflective sheet designed to be propelled by radiation pressure, could exhibit exactly the acceleration patterns observed in ʻOumuamua. While the scientific community largely rejected this hypothesis, it highlighted how far outside normal parameters the object's behavior had pushed astronomical thinking. The acceleration anomaly also had implications for our understanding of interstellar space itself. If ʻOumuamua represented a typical interstellar object, it suggested that the space between stars might be populated by bodies with properties completely different from anything in our solar system. The acceleration anomaly also had implications for our understanding of interstellar space itself. If ʻOumuamua were represented a typical interstellar object, it suggested that the space between stars might be populated by bodies with properties completely different from anything in our solar system. This would revolutionize our understanding of planetary formation, stellar evolution, and the distribution of matter in the galaxy. 1 Dr. Alan Fitzsimmons from Queen's University Belfast noted the epistemological challenge. ʻOumuamua is forcing us to confront the limits of our knowledge. We're discovering that the universe might be stranger and more diverse than we ever imagined. The object had become a mirror, reflecting back the assumptions and limitations of human understanding. The implications reached into the future of astronomy itself. If objects like ʻOumuamua were common in interstellar space, it meant that our solar system was regularly visited by entities that might not conform to our theoretical models. This required new observational strategies, new theoretical frameworks, and perhaps even new physics to understand. The acceleration anomaly also highlighted the importance of rapid response in astronomical observations. ʻOumuamua's brief visit had provided only a small window of opportunity to study its properties, and many crucial questions remained unanswered because the object had faded from view before comprehensive observations could be completed. This experience would influence how astronomers prepared for future interstellar visitors. Perhaps most profoundly, ʻOumuamua mysterious acceleration served as a reminder that the universe still held surprises that could challenge our most fundamental assumptions. In an age when many aspects of physics seemed well established, this small object had managed to inject genuine mystery back into astronomy, proving that discovery and wonder were far from exhausted in our exploration of the cosmos. Withdraw many aspects of physics seemed dull. In the spring of 2020, as the scientific community continued to grapple with ʻOumuamua's inexplicable acceleration, a young postdoctoral researcher at the University of Chicago proposed what would become one of the most radical and controversial explanations for the mysterious visitor. Dr. Darrell Seligman, working with Professor Gregory Laughlin, published a paper that would fundamentally challenge our understanding of what materials could exist in the frozen depths of interstellar space. The hydrogen hypothesis emerged from a simple but profound question. What if ʻOumuamua was made of a material so exotic that it had never been seriously considered as a building block for celestial objects? Seligman's calculations suggested that if the mysterious visitor were composed primarily of solid hydrogen, frozen at temperatures approaching absolute zero, it could explain both the object's bizarre acceleration and its seemingly contradictory properties. The theory was breathtakingly audacious. Hydrogen is the lightest and most abundant element in the universe, but it exists as a solid only under the most extreme conditions. At normal atmospheric pressure, hydrogen freezes at -259 degrees Celsius, just 14 degrees above absolute zero. More importantly, solid hydrogen is extraordinarily fragile. It would sublimate directly from solid to gas at the slightest warming, potentially providing the invisible propulsion that was accelerating ʻOumuamua away from the sun. Dr. Seligman's models showed that a hydrogen iceberg could exhibit precisely the acceleration pattern observed in ʻOumuamua. As the object approached the sun, solar radiation would cause the outermost layers of solid hydrogen to sublimate, creating jets of invisible hydrogen gas that would act like tiny rocket engines. The process would be completely undetectable to our instruments because hydrogen gas is transparent across most of the electromagnetic spectrum. The mathematics were elegant and compelling. A solid hydrogen object with ʻOumuamua's estimated size could produce enough thrust through sublimation to match the observed acceleration exactly. The force would be strongest near the sun, then gradually weaken as the object moved away and cooled, precisely matching the pattern detected in the Hubble observations. But the hydrogen hypothesis immediately faced a seemingly insurmountable challenge. How could such an object possibly survive in space? Or Dr. Abraham Loeb from Harvard University articulated the central problem. Solid hydrogen has a sublimation temperature that's only slightly above absolute zero, Even the minimal heat sources in interstellar space should cause such an object to evaporate completely long before it could reach our solar system. Seligman and Laughlin had anticipated this criticism. Their calculations showed that if a hydrogen iceberg were large enough initially, perhaps several kilometers in diameter, it could indeed survive a journey of millions of years through interstellar space. Macwin D. from Ingapuru. Seligman and Laughlin had anticipated this criticism. The outer layers would continuously sublimate away, but the inner core would remain frozen, insulated by the vacuum of space and the object's own large thermal mass. The researchers proposed that such hydrogen icebergs could form in the outer regions of planetary systems, where temperatures are cold enough for hydrogen to condense and freeze. These primordial objects could then be ejected into interstellar space by gravitational interactions with massive planets, beginning epic journeys that might last millions of years across the galaxy. The theory also explained ʻOumuamua's unusual shape and properties. As the hydrogen iceberg traveled through space, it would lose mass through continuous sublimation, potentially creating the extreme elongation observed in the object. The process would also naturally explain the lack of visible outgassing. Hydrogen gas is nearly transparent and would be impossible to detect with conventional astronomical instruments. Dr. Michaeli Bannister from the University of Canterbury found the theory intriguing but challenging. The hydrogen hypothesis is mathematically elegant, but it requires us to accept that solid hydrogen objects can exist and travel through space for millions of years. That's a huge leap from our current understanding of materials in extreme environments. The implications of the hydrogen hypothesis extended far beyond explaining ʻOumuamua's behavior. If solid hydrogen objects could indeed exist in interstellar space, it would suggest that the galaxy might be populated by an entirely unknown class of celestial bodies. These hydrogen icebergs could represent a significant fraction of the dark matter in the universe, invisible to our instruments, but carrying substantial mass as they drift between the stars. The theory also raised fascinating questions about the formation and evolution of planetary systems. If hydrogen icebergs were common, they might play important roles in delivering hydrogen to rocky planets, potentially contributing to the formation of atmospheres and even the development of life. The discovery of such objects would revolutionize our understanding of how materials are distributed throughout the galaxy. Seligman himself acknowledged the revolutionary nature of the proposal. We're essentially suggesting that there's an entire population of objects in the galaxy that we've never recognized before. These hydrogen icebergs could be everywhere, but we've never seen them because they're invisible until they happen to pass close to a star. The hydrogen hypothesis represented a perfect example of how genuinely mysterious phenomena can force science to consider possibilities that seem impossible at first glance. Whether or not the theory would ultimately prove correct, it had already achieved something remarkable. It had expanded the boundaries of what astronomers considered possible in the universe. The hydrogen iceberg theory required a deep dive into the exotic physics of matter at temperatures approaching absolute zero. To understand whether ʻOumuamua could truly be a solid hydrogen object, scientists had to explore the behavior of materials under conditions so extreme that they had rarely been studied in terrestrial laboratories. The resulting investigation would reveal both the theoretical elegance and the practical challenges of Seligman's radical proposal. Solid hydrogen exists in a realm of physics that most scientists rarely encounter. At atmospheric pressure, hydrogen freezes at -259 degrees Celsius, creating a substance with properties unlike any common material. Isaac Silver, from Harvard University, one of the world's leading experts on solid hydrogen, explained the extraordinary nature of this material. Solid hydrogen is essentially a quantum solid. Its properties are dominated by quantum mechanical effects rather than classical physics, making it behave in ways that can seem counterintuitive. The density of solid hydrogen is remarkably low, only about 0.09 grams per cubic centimeter, making it lighter than cork and less than 1/10 the density of water. This ultra-low density was actually a crucial advantage for the hydrogen iceberg theory. An object made of solid hydrogen would have an enormous surface area relative to its mass, maximizing the effects of both solar radiation pressure and outgassing-induced acceleration. Dr. Seligman's calculations showed that ʻOumuamua's observed acceleration could be explained if the object were losing mass through hydrogen sublimation at a rate of about 10 circumflex 6 solar masses per second, roughly equivalent to 2 billion kilograms per second. While this sounds enormous, it represented only a tiny fraction of the object's total mass, assuming it were composed primarily of solid hydrogen. The sublimation process itself was key to understanding how the acceleration worked. As solar radiation heated the surface of the hydrogen iceberg, the outermost layers would transition directly from solid to gas without passing through a liquid phase. This sublimation would be completely invisible to our instruments because hydrogen gas is transparent across most of the electromagnetic spectrum, unlike the dust and water vapor that make comet tails visible. The directional nature of the sublimation was crucial for producing the observed acceleration. Dr. Zdeněk Sekanina from JPL created detailed models showing how uneven heating of a rotating elongated object generated asymmetric outgassing patterns. The directional nature of the sublimation was crucial for producing the observed acceleration. These patterns would act like rocket nozzles, pushing the object in specific directions relative to the sun. The models demonstrated that such a process could indeed produce the acceleration pattern observed in ʻOumuamua. But the theory faced significant challenges when scientists examined the thermal properties of solid hydrogen. Dr. Eugene Chang from UC Berkeley pointed out a fundamental problem. Solid hydrogen has extremely high thermal conductivity. Any heat absorbed at the surface would quickly spread throughout the object, potentially causing catastrophic disintegration rather than controlled sublimation. The thermal conductivity issue was particularly problematic for understanding how a hydrogen iceberg could survive its approach to the sun. As ʻOumuamua came within 0.25 astronomical units of our star, its surface temperature would have risen to hundreds of degrees Kelvin, far above the sublimation point of solid hydrogen. The rapid heat conduction through the object should have caused it to disintegrate completely rather than maintain its coherent structure. Seligman and Laughlin addressed these concerns by proposing that the hydrogen iceberg might have a protective surface layer of more refractory materials. This crust could be composed of heavier molecules that had frozen onto the hydrogen core during its formation or journey through space. Such a layer could regulate the sublimation process, allowing controlled outgassing while preventing catastrophic disintegration. The formation mechanism for hydrogen icebergs presented another theoretical challenge. Dr. Konstantin Batygin from Caltech investigated how such objects could form in the outer regions of planetary systems. His models suggested that hydrogen icebergs could condense in the extremely cold environments around giant planets, where temperatures drop below 10⁻20 Kelvin. These objects could then be ejected into interstellar space by gravitational interactions with the planets themselves. The survival of hydrogen icebergs during interstellar travel required careful consideration of the thermal environment between stars. While interstellar space is extremely cold, typically around 2.7 Kelvin, it's not a perfect vacuum. Cosmic rays, starlight from distant stars, and collisions with interstellar dust grains all contribute small amounts of energy that could gradually erode a hydrogen iceberg over millions of years. Dr. Amaya Moro-Martin from the Space Telescope Science Institute calculated the erosion rates for hydrogen icebergs during interstellar travel. Her models showed that while such objects would indeed lose mass continuously, they could potentially survive journeys of millions of years if they began with sufficient initial mass, perhaps 10⁻100 times larger than ʻOumuamua's observed size. The isotopic composition of hydrogen icebergs presented another avenue for testing the theory. Different stellar environments produce hydrogen with slightly different isotopic ratios, and these signatures could potentially be detected if a hydrogen iceberg were to outgas near Earth. Unfortunately, the ʻOumuamua's rapid departure made such measurements impossible, but future interstellar visitors might provide opportunities for isotopic analysis. The implications of the hydrogen iceberg theory extended beyond explaining ʻOumuamua's behavior. If such objects were common in interstellar space, they could represent a significant reservoir of hydrogen in the galaxy. Dr. Gregory Laughlin estimated that the total mass of hydrogen icebergs might be comparable to the mass of stars themselves, making them a major component of the galaxy's baryonic matter budget. The theory also raised questions about the role of hydrogen icebergs in planetary formation. If these objects were regularly captured by forming stellar systems, they could contribute significant amounts of hydrogen to the atmospheres of rocky planets. This process might help explain how planets like Earth acquired their atmospheric hydrogen, which is essential for the formation of water and organic molecules. Perhaps most intriguingly, the hydrogen iceberg theory suggested that the galaxy might be filled with objects that are essentially invisible until they happen to pass close to a star. These dark comets could represent an entire population of interstellar travelers that we've never recognized before. The discovery of such objects would revolutionize our understanding of the distribution of matter in the galaxy and the processes that shape planetary systems. The physics of frozen hydrogen had revealed both the theoretical possibility and the practical challenges of the hydrogen iceberg theory. While the mathematics were elegant and the predictions matched observations, the extreme conditions required for such objects to exist and survive pushed the boundaries of what scientists considered plausible in the universe. Part 5. C. Problems with Paradise. The theory's weaknesses. 750 words. Despite its mathematical elegance and ability to explain ʻOumuamua's mysterious acceleration, the hydrogen iceberg theory faced a barrage of criticism from the scientific community. As researchers scrutinized the proposal more closely, they uncovered a series of fundamental problems that challenged the theory's viability and forced proponents to defend assumptions that seemed increasingly difficult to justify. The most immediate criticism came from experts in solid hydrogen physics. Russell Hemley from the University of Illinois, a leading authority on materials under extreme conditions, pointed out that the theory required solid hydrogen to behave in ways that had never been observed in laboratory experiments. "We've studied solid hydrogen extensively under various conditions," he explained, "and its behavior is quite different from what the ʻOumuamua theory requires. The material is extremely fragile and would likely disintegrate under the thermal and mechanical stresses of interstellar travel." The thermal stability problem proved particularly troublesome. Thiam Hoeying from the Korea Astronomy and Space Science Institute published detailed calculations showing that even the minimal heat sources in interstellar space would cause a hydrogen iceberg to evaporate completely within a few million years. His models indicated that cosmic ray heating, collisions with interstellar dust, and radiation from distant stars would provide enough energy to sublime away any hydrogen object long before it could reach our solar system. The formation mechanism for hydrogen icebergs also came under intense scrutiny. Dr. Anders Johansson from Lund University in Sweden challenged the idea that such objects could form in the outer regions of planetary systems. His research on planet formation showed that while hydrogen is abundant in these regions, the conditions necessary for large-scale hydrogen condensation are extremely rare and short-lived. The window for forming kilometer-sized hydrogen icebergs appears to be essentially zero, he concluded. Even more problematic was the question of how hydrogen icebergs could survive ejection from their parent star systems. Dr. Hull Leveson from the Southwest Research Institute demonstrated that the gravitational interactions required to eject objects into interstellar space would subject them to enormous tidal forces. These forces would likely tear apart any object as fragile as a hydrogen iceberg, preventing them from beginning their interstellar journeys intact. The isotopic composition of hydrogen presented another challenge to the theory. Dr. Daryl Seligman had proposed that hydrogen icebergs could form around different types of stars, each producing hydrogen with slightly different isotopic ratios. However, Dr. Edwin Bergin from the University of Michigan pointed out that the isotopic signatures of hydrogen in different stellar environments are not as distinctive as the theory required. This made it difficult to use isotopic analysis as a test of the hydrogen iceberg hypothesis. The survival statistics for hydrogen icebergs during interstellar travel also proved problematic. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy calculated that if hydrogen icebergs were common enough to explain ʻOumuamua appearance in our solar system, they would need to be produced in enormous quantities by other star systems. His models suggested that virtually every star in the galaxy would need to eject thousands of hydrogen icebergs throughout its lifetime, a production rate that seemed astronomically implausible. The observational predictions of the hydrogen iceberg theory also faced challenges. Dr. Alan Fitzsimmons from Queen's University Belfast noted that if ʻOumuamua were indeed a hydrogen iceberg, it should have shown detectable changes in its spectral properties as it sublimated. A hydrogen iceberg should become progressively more reflective as it loses its outer layers, he explained. We saw no such changes in ʻOumuamua's spectrum, which remained remarkably constant throughout our observations. The theory's predictions about the object's structure and density were also questioned. Dr. Zdeněk Šekanina from JPL calculated that a hydrogen iceberg with ʻOumuamua's observed properties would need to have an implausibly complex internal structure to explain its rotation and brightness variations. The object would need to be both extremely lightweight and structurally coherent, a combination that seemed difficult to achieve with solid hydrogen. Perhaps most damaging to the theory was the lack of any observational evidence for hydrogen icebergs elsewhere in the universe. Despite decades of astronomical observations, no other objects had been identified that showed the characteristics predicted for hydrogen icebergs. This absence of supporting evidence made many scientists skeptical that such objects existed at all. The criticism culminated in a series of papers that systematically dismantled the hydrogen iceberg theory's key assumptions. While the theory had been mathematically elegant and internally consistent, it appeared to require conditions and processes that were either extremely rare or entirely unprecedented in our understanding of the universe. The scientific community was forced to continue its search for explanations of ʻOumuamua's mysterious behavior. In the normally conservative world of academic astronomy, few scientists are willing to risk their reputations by proposing ideas that venture into the realm of science fiction. But in late 2018, as conventional explanations for ʻOumuamua's behavior continued to fall short, one of Harvard University's most distinguished astrophysicists decided to voice what many of his colleagues were thinking, but dared not say aloud. What if this mysterious visitor wasn't natural at all? Dr. Abraham A.V. Loeb, chair of Harvard's astronomy department and one of the most cited theoretical astrophysicists in the world, had built his career on solid scientific ground. On Cephas and Cepheid, his research on black holes, the early universe, and the search for extraterrestrial life had earned him international recognition and made him a trusted voice in the scientific community, which is precisely why his proposal about ʻOumuamua sent shockwaves through the astronomical world. In a paper published in the astrophysical journal Letters, Loeb and his postdoctoral researcher, Shmuel Bialy, presented a hypothesis that would ignite one of the most heated debates in modern astronomy. They suggested that ʻOumuamua's unusual properties, its extreme elongation, its mysterious acceleration, and its lack of visible outgassing were all consistent with artificial technology from another civilization. The seed of this radical idea had been planted months earlier during a casual conversation between Loeb and his colleague. We were discussing the acceleration problem, Loeb recalled, and I mentioned that the only way to explain such behavior without visible outgassing would be if the object had an extremely large surface area relative to its mass. That's when it hit me. We were essentially describing a light sail. Light sails, also known as solar sails, are a well-established concept in space exploration. These gossamer-thin sheets of reflective material can be propelled through space by the gentle pressure of sunlight, requiring no fuel and capable of achieving enormous speeds over time. Several space agencies, including NASA and Japan's JAXA, have successfully deployed light sails on interplanetary missions, proving that the technology works in practice. But Loeb's proposal went far beyond conventional light sails. He suggested that ʻOumuamua might be a probe or derelict piece of technology from an alien civilization, perhaps a reconnaissance device designed to study our solar system, or the remnant of some ancient spacecraft that had been drifting through interstellar space for millennia. The mathematics were compelling. An artificial light sail with ʻOumuamua's observed dimensions would need to be incredibly thin, perhaps only a few hundred nanometers thick, to explain the acceleration without visible propulsion. This thickness was comparable to soap bubbles or spider silk, yet the object would need to be hundreds of meters long to match the size estimates derived from brightness observations. Such extreme dimensions would give the object an enormous surface area to mass ratio, making it exquisitely sensitive to radiation pressure from the sun. As solar photons struck the sail's surface, they would impart momentum that could accelerate the object in precisely the manner observed. The acceleration would be strongest near the sun, then gradually weaken as the object moved away, exactly matching ʻOumuamua's behavior. The artificial hypothesis also explained other puzzling aspects of the object's characteristics. The extreme elongation, which seemed almost impossible for a natural object, would be perfectly reasonable for an artificial structure. The lack of visible outgassing was expected if the object were made of engineered materials rather than ice and rock. Even the tumbling motion could be explained as the result of structural damage or the natural evolution of an uncontrolled artificial object drifting through space. Loeb was careful to present his hypothesis within the framework of rigorous scientific methodology.
I'm not claiming that ʻOumuamua is definitely artificial, he emphasized. I'm simply pointing out that we cannot rule out this possibility based on the available evidence. In science, we should consider all hypotheses that are consistent with the data, even if they seem uncomfortable or unlikely.
The timing of Loeb's proposal was significant. The astronomical community had spent months struggling to explain ʻOumuamua behavior using conventional physics, and every proposed solution had encountered serious problems. The hydrogen iceberg theory faced thermal stability issues. Radiation pressure explanations couldn't account for the magnitude of acceleration, and outgassing models failed to match the lack of visible activity. In this context, Loeb's artificial hypothesis represented a kind of scientific shock therapy, a deliberate attempt to force the community to confront the limitations of their assumptions. Sometimes in science, he explained, we need to be willing to think the unthinkable. If we only consider explanations that fit comfortably within our existing paradigms, we might miss genuinely revolutionary discoveries.
Zeres wall, my trendo, fuaris praise, Usemdia peris praise, a deliberate attempt to force the community to confront the limitations of their assumptions. Sometimes in science, he explained, we need to be willing to think the unthinkable.
The proposal gained additional credibility from Loeb's impeccable scientific credentials. Unlike fringe theorists who often promote extraterrestrial explanations, Loeb was a mainstream scientist with a distinguished publication record and a reputation for careful, methodical research. His willingness to stake his reputation on such a controversial idea signaled that the ʻOumuamua mystery had reached a point where even the most conservative scientists were being forced to consider radical possibilities. The artificial hypothesis also resonated with broader trends in astronomy and astrobiology. The discovery of thousands of exoplanets had made it clear that planetary systems were common throughout the galaxy, and many of these systems were billions of years older than our own. If intelligent life had evolved in any of these ancient systems, they would have had enormous amounts of time to develop advanced technology and explore the galaxy. From this perspective, the appearance of artificial objects in our solar system wasn't just possible, it was almost inevitable. The galaxy is about 10 billion years old, Loeb noted. If technological civilizations arose even once in a million star systems, and if they developed interstellar travel capabilities, then artificial objects should be passing through our solar system regularly. The hypothesis also aligned with theoretical work on the long-term evolution of technological civilizations. Some researchers had proposed that advanced civilizations might launch large numbers of probes to explore the galaxy, creating a network of artificial objects that could persist for millions of years. ʻOumuamua could represent our first encounter with such a probe, whether it was still functional or had become derelict after eons of interstellar travel. But Loeb's proposal came with a crucial caveat. The artificial hypothesis was essentially unfalsifiable with the available data. ʻOumuamua had already disappeared into the outer solar system, and no existing or planned telescopes would be able to observe it again. This meant that the artificial hypothesis would remain forever speculative unless similar objects were discovered in the future. The unfalsifiability of the proposal made it both scientifically honest and deeply frustrating. Loeb was acknowledging that the evidence was insufficient to definitively prove artificial origin, but he was also pointing out that it was insufficient to rule it out. This left the scientific community in an uncomfortable position, forced to grapple with a hypothesis that could neither be confirmed nor refuted. The artificial hypothesis also raised profound questions about the nature of scientific conservatism. Throughout history, many revolutionary discoveries had initially been dismissed because they challenged established paradigms. The idea that scientists should seriously consider artificial explanations for astronomical phenomena was itself a kind of paradigm shift, forcing the community to expand their conception of what constituted legitimate scientific inquiry. As news of Loeb's proposal spread beyond the scientific community, it captured the public imagination in ways that few astronomical discoveries had achieved. The possibility that humanity's first confirmed interstellar visitor might be artificial technology touched on deep questions about our place in the universe and the prevalence of intelligent life. The hypothesis transformed ʻOumuamua from a scientific curiosity into a cultural phenomenon, inspiring countless articles, documentaries, and speculative discussions about the implications of contact with alien technology. The technical foundation of Loeb's artificial hypothesis rested on a sophisticated understanding of how radiation pressure could propel objects through space. To build a convincing case for ʻOumuamua's artificial origin, he needed to demonstrate that the observed acceleration could be explained by a light sail of plausible dimensions and properties, a challenge that required diving deep into the physics of photon momentum and materials science. The fundamental principle behind light sails is elegantly simple. Photons, despite having no mass, carry momentum that can be transferred to objects they strike. When sunlight hits a reflective surface, it imparts a tiny push, so small that it's usually negligible, but potentially significant for objects with large surface areas and low masses. This radiation pressure is what creates the beautiful tails of comets, pushing dust and gas away from their nuclei as they approach the sun. Dr. Loeb's calculations showed that for radiation pressure to explain ʻOumuamua's acceleration, the object would need to have a surface area to mass ratio of approximately 20 square meters per kilogram. This was an extraordinary requirement, roughly 20 times higher than typical asteroids or comets. To achieve such a ratio, the object would need to be either extremely lightweight or have an enormous surface area relative to its volume. The mathematics pointed toward a flat, sheet-like structure rather than a compact, three-dimensional object. If ʻOumuamua were indeed a light sail, it would need to be incredibly thin, perhaps only a few hundred nanometers thick, comparable to the thickness of a soap bubble. At this thickness, a sail with the observed dimensions of roughly 400 meters by 40 meters would have a mass of only about 60,000 kilograms, giving it exactly the surface area to mass ratio needed to explain the acceleration. The technical requirements for such a structure were staggering. The sail material would need to be strong enough to maintain its integrity during millions of years of interstellar travel, yet lightweight enough to be accelerated by radiation pressure. It would need to be reflective enough to efficiently convert photon momentum into thrust, yet resistant to the cumulative effects of cosmic ray bombardment and micrometeorite impacts. Dr. Loeb explored various materials that might meet these requirements. Graphene, a single layer of carbon atoms arranged in a hexagonal lattice, had the necessary strength and lightness. Advanced metamaterials, engineered at the nanoscale to have properties not found in nature, could potentially be even more suitable. Some proposed materials existed only in theoretical models, but they demonstrated that the technical requirements were at least physically plausible. The orientation and stability of the light sail presented another layer of complexity. For radiation pressure to produce the observed acceleration pattern, the sail would need to maintain a relatively stable orientation relative to the Sun throughout its passage through the solar system. This required either active control systems or a carefully designed passive structure that would naturally orient itself in the solar wind. The tumbling motion observed in ʻOumuamua actually supported the artificial hypothesis in unexpected ways. Loeb's models showed that a damaged or derelict light sail would naturally evolve into a tumbling state over time, as small asymmetries in radiation pressure and the object's structure would gradually destabilize its orientation. The complex rotation pattern could be the signature of an artificial object that had lost its guidance systems long ago. The extreme elongation that had puzzled astronomers since ʻOumuamua's discovery suddenly made perfect sense. If the object were artificial, while natural processes struggle to create objects with aspect ratios of 5 or 10, artificial structures could easily be designed with such proportions. A light sail would naturally be elongated to maximize its surface area while minimizing structural complexity. The timing of the acceleration also fit the artificial hypothesis perfectly. The non-gravitational force was strongest when ʻOumuamua was closest to the Sun, exactly as expected for radiation pressure. As the object moved away and the intensity of sunlight decreased, the acceleration gradually weakened, a pattern that would be automatic for any light sail, regardless of its origin or control systems. Dr. Loeb also considered how such an object might have originated. Advanced civilizations might deploy light sails as reconnaissance probes, designed to visit multiple star systems and gather information about planetary systems and potential life. Such probes could be programmed to follow complex trajectories, using radiation pressure and gravity assists to visit numerous targets over millions of years. Alternatively, ʻOumuamua might be a piece of debris from some larger artificial structure, perhaps a derelict spacecraft, or the remnant of an ancient solar sail that had been torn apart by tidal forces or collisions. The galaxy might be littered with such technological artifacts, the remnants of civilizations that had explored interstellar space millions of years ago. The artificial hypothesis also made specific predictions about what astronomers might expect to find in similar objects. If ʻOumuamua were indeed artificial, there should be other examples of interstellar objects with similar properties. These objects might show evidence of engineered materials, unusual isotopic ratios, or other signatures that would be difficult to explain through natural processes. The technical case for artificial origin was strengthened by the absence of alternative explanations. Every proposed natural mechanism for ʻOumuamua's acceleration faced significant problems, from the thermal instability of hydrogen icebergs to the implausible outgassing rates required for invisible comet-like activity. The artificial hypothesis, while extraordinary, was at least internally consistent and technically feasible. Dr. Loeb was careful to acknowledge the limitations of his technical analysis. We cannot prove that ʻOumuamua is artificial based on the available evidence, he emphasized. But we can demonstrate that artificial origin is consistent with all the observed properties, and that the technical requirements are within the realm of possibility for an advanced civilization. The technical case also raised intriguing questions about the detection and study of artificial objects in space. If such objects were indeed present in our solar system, they would require new observational strategies and analysis techniques. Traditional asteroid and comet studies might be inadequate for understanding objects that operated according to engineering principles rather than natural physics. Perhaps most importantly, the technical analysis had demonstrated that the artificial hypothesis was not just wild speculation, but a serious scientific proposition, supported by rigorous calculations and physical reasoning. Whether or not ʻOumuamua was actually artificial, Loeb had shown that such objects could exist, and that we might be able to recognize them if we knew what to look for. The reaction to Loeb's artificial hypothesis was swift, intense, and revealed the deep philosophical divisions within the scientific community about how to approach extraordinary claims. Within days of the paper's publication, astronomers around the world began publishing responses that ranged from measured skepticism to harsh criticism, creating one of the most public displays of scientific peer review in recent memory. Dr. Alan Fitzsimmons from Queen's University Belfast led the charge against the artificial hypothesis with a paper titled Visia Online Data Catalogue. ʻOumuamua is tumbling. His team's analysis focused on the object's rotation state, arguing that the tumbling motion was inconsistent with a functional light sail, but perfectly consistent with a natural object that had been subjected to collisions or other disruptive forces during its journey through space. Disruptive forces during its journey through space. The tumbling we observe is exactly what we'd expect from a natural object, Fitzsimmons explained. A functioning light sail would need to maintain a stable orientation relative to the sun to achieve efficient propulsion. The chaotic rotation we see suggests either a severely damaged artificial object or, more likely, a natural body that has been knocked around by impacts over millions of years. The criticism intensified when Dr. Marco Micheli from the European Space Agency published a detailed reanalysis of ʻOumuamua's trajectory. His calculations showed that while the artificial hypothesis could explain the observed acceleration, it required the object to have properties that were at the extreme edge of what was physically possible. The light sail explanation works mathematically, Micheli acknowledged, but it requires such an unusual combination of properties that it seems far less likely than natural explanations we haven't yet discovered. Perhaps the most damaging criticism came from experts in materials, science and engineering. Dr. Zdenek Sekanina from JPL argued that no known material could survive the conditions required for Loeb's hypothesis to work. A light sail thin enough to be accelerated by radiation pressure would be incredibly fragile, he pointed out. The thermal stresses alone from passing near the sun would likely destroy such a structure, not to mention the accumulated damage from millions of years of cosmic ray bombardment. The scientific backlash also revealed deeper concerns about the methodology and philosophy of the artificial hypothesis. Catherine Fries from the University of Michigan articulated a common concern. While we should certainly keep an open mind about the possibility of artificial objects, we also need to be extremely careful about invoking extraordinary explanations before we've exhausted all natural possibilities. This criticism touched on a fundamental principle of scientific reasoning known as Occam's razor, the idea that the simplest explanation that fits the evidence is usually correct. Many scientists argued that proposing artificial origin for ʻOumuamua violated this principle by invoking complex scenarios involving advanced alien civilizations when simpler natural explanations might still be found. The debate also highlighted the challenge of falsifiability in scientific hypotheses. Dr. Paul Davies from Arizona State University, himself a proponent of searching for alien technology, noted that the artificial hypothesis is essentially untestable with current technology. We can't prove it's wrong, but we also can't prove it's right. This makes it more of a philosophical position than a scientific theory. The controversy extended beyond the scientific community when several prominent astronomers accused Loeb of seeking publicity rather than advancing serious scientific inquiry. Robert Werrick, who had discovered ʻOumuamua, expressed frustration with the artificial hypothesis. This object is already mysterious enough without adding speculation about alien technology. We should focus on understanding what we can actually observe and measure. However, the backlash wasn't universal. Some scientists defended Loeb's right to propose unconventional explanations, arguing that the astronomical community was being too conservative in its thinking. Jill Tarter, former director of the SETI Institute, supported the artificial hypothesis. If we're serious about searching for extraterrestrial intelligence, we need to be willing to consider the possibility that we might actually find it. Dismissing artificial explanations out of hand is just as unscientific as accepting them uncritically. The peer review process also revealed the difficulty of maintaining scientific objectivity when dealing with topics that capture public imagination. The artificial hypothesis had generated enormous media attention, and some scientists worried that this publicity was influencing the scientific debate in unhealthy ways. Despite the intense criticism, Loeb remained steadfast in his position. Science is not a popularity contest. he responded to his critics. The strength of an idea should be judged by its consistency with the evidence, not by how comfortable it makes us feel. If the evidence points toward artificial origin, we should seriously consider that possibility regardless of its implications. The scientific backlash had revealed both the strengths and weaknesses of the peer review process, demonstrating how the scientific community grapples with ideas that challenge fundamental assumptions about the nature of the universe. Determining where ʻOumuamua came from required one of the most complex exercises in celestial detective work ever attempted. Unlike objects that orbit the sun, which follow predictable elliptical paths, this interstellar visitor had traveled through space for millions of years, its trajectory shaped by the gravitational influences of countless stars, planets, and other massive objects. Tracing its path backward through time was like following a cosmic breadcrumb trail that led deep into the galaxy's past. Dr. Corinne Baylor-Jones, from the Max Planck Institute for Astronomy, led the most comprehensive investigation into ʻOumuamua's origin. Using data from the European Space Agency's Gaia mission, which had precisely measured the positions and velocities of over 1 billion stars, his team attempted to reconstruct the object's journey through the galaxy. The task required sophisticated computer simulations that could model gravitational interactions over millions of years. The fundamental challenge was that ʻOumuamua's trajectory had to be calculated backward through time, accounting for the gravitational influences of every significant mass the object had encountered during its journey. This included not just stars, but also massive planets, brown dwarfs, and even the subtle effects of the galaxy's overall gravitational field. Each gravitational encounter would have slightly altered the object's path, creating a complex web of influences that stretched back through cosmic history. The calculations revealed that ʻOumuamua's motion through the galaxy was remarkably close to what astronomers call the local standard of rest, essentially the average motion of stars in our region of the galaxy. This suggested that the object had not been dramatically accelerated by any recent gravitational encounters, but had instead been drifting through space at a relatively constant velocity for an extended period. Dr. Baylor-Jones's models showed that tracing the trajectory beyond about 1 million years became increasingly uncertain due to the cumulative effects of small gravitational perturbations. However, the team was able to identify several stars that ʻOumuamua had passed relatively close to in the recent past. These stellar encounters provided crucial clues about the object's possible origin. The most intriguing finding was that ʻOumuamua's path could be traced back to a close encounter with a red dwarf star in the constellation Lyra. The object had passed within about 1.4 light-years of this star, close enough for gravitational interactions to have significantly influenced its trajectory. This suggested that the star might have been ʻOumuamua's last major gravitational encounter before entering our solar system. But the investigation revealed a crucial limitation. The precision of stellar position and velocity measurements wasn't sufficient to definitively identify ʻOumuamua's parent star system. Even with Gaia's unprecedented accuracy, uncertainties in stellar motions accumulated over millions of years, making it impossible to pinpoint the object's exact origin with certainty. The trajectory analysis also provided insights into the broader population of interstellar objects. Dr. Baylor-Jones calculated that for ʻOumuamua to have appeared in our solar system, there must be an enormous number of similar objects drifting through interstellar space. The trajectory analysis also provided insights into the broader population of interstellar objects. Dr. Baylor-Jones calculated that for ʻOumuamua to have appeared in our solar system, his models suggested that the space between stars might contain trillions of such objects, most of them too small and distant to be detected by current telescopes. The origin investigation faced additional complications when scientists realized that ʻOumuamua's mysterious acceleration might have altered its trajectory in ways that weren't accounted for in the gravitational models. If the object had been accelerating throughout its journey, due to outgassing or other non-gravitational forces, its original path might have been significantly different from what could be calculated using purely gravitational dynamics. Dr. Davide Farnocchia from NASA's Jet Propulsion Laboratory attempted to address this problem by incorporating the acceleration effects into the trajectory calculations. His analysis suggested that the non-gravitational acceleration observed near the Sun might represent a continuous process that had been operating throughout ʻOumuamua journey. This would make the object's origin even more difficult to determine, as its path would have been continuously altered by forces that left no clear observational signature. The investigation also revealed the importance of the object's initial velocity when it entered our solar system. ʻOumuamua was traveling at about 26 kilometers per second relative to the Sun, fast enough to escape the solar system, but not so fast as to suggest a highly energetic ejection from its parent star. This velocity was consistent with objects that had been ejected from planetary systems by gravitational interactions with giant planets, rather than by more violent processes like stellar explosions. The trajectory work highlighted the need for better observational data on interstellar objects. Future surveys like the Vera-Rubin Observatory would need to detect such objects much earlier in their approach to the solar system, providing more time for detailed observations and more precise trajectory determinations. Only with better data could astronomers hope to definitively trace the origins of interstellar visitors. Perhaps most importantly, the trajectory analysis had revealed that ʻOumuamua was not unique. It was likely representative of a vast population of interstellar objects that regularly pass through our solar system. The challenge was not just understanding where this particular object came from, but recognizing that our solar system was part of a much larger, more dynamic galactic environment than previously imagined. Among the hundreds of stars that ʻOumuamua had passed during its journey through the galaxy, one stood out with particular significance. Vega, the brilliant blue-white star that serves as the northern pole star in the constellation Lyra. The potential connection between our mysterious visitor and this iconic star would provide astronomers with their strongest clue about ʻOumuamua's possible origin and raise profound questions about the nature of planetary systems around other stars. Dr. Corinne Baylor-Jones's trajectory analysis revealed that approximately 300,000 years ago, ʻOumuamua had passed within about 1.8 light-years of Vega, a distance that, while enormous by terrestrial standards, was close enough for significant gravitational interactions in the context of interstellar space. This close encounter had likely altered the object's trajectory, but it also suggested that Vega might have been ʻOumuamua's most recent stellar neighborhood before its journey to our solar system. The Vega connection was particularly intriguing because this star had long been a subject of intense astronomical interest. Located just 25 light-years from Earth, Vega is one of the brightest stars in our night sky and has served as a calibration standard for stellar brightness measurements. But beyond its prominence in earthly astronomy, Vega represented something far more significant. It was one of the first stars around which astronomers had discovered clear evidence of a planetary system in formation. In the 1980s, infrared observations from the Infrared Astronomical Satellite, IRAS, had revealed that Vega was surrounded by a disk of dust and debris, the telltale signature of a young planetary system. This discovery had revolutionized our understanding of planet formation, providing the first direct evidence that planetary systems were common around other stars. The Vega disk became a prototype for understanding how planets form from the collapse of dusty disks around young stars. Dr. Kate Su, from the University of Arizona, who had studied the Vega system extensively, noted the significance of the potential connection. If ʻOumuamua did indeed originate from the Vega system, it would represent our first direct sample of material from another star's planetary formation process. This could provide unprecedented insights into how planetary systems form and evolve. The age of the Vega system added another layer of complexity to the origin story. At approximately 455 million years old, Vega was much younger than our Sun, which is about 4.6 billion years old. This meant that if ʻOumuamua had originated from the Vega system, it would have been ejected during a relatively early phase of that system's evolution, possibly during the chaotic period when planets were still forming and migrating. The process of planetary system formation is inherently violent and dynamic. As planets grow and migrate through their systems, they can gravitationally scatter smaller objects, ejecting them into interstellar space. The Vega system, with its observed debris disk and likely ongoing planet formation processes, would have been an ideal environment for producing interstellar objects like ʻOumuamua. However, the Vega connection faced significant challenges. The trajectory calculations, while suggestive, were not precise enough to definitively establish the star as ʻOumuamua's origin. The uncertainties in stellar positions and velocities over hundreds of thousands of years made it impossible to prove that the object had actually originated from the Vega system rather than simply passing through its neighborhood. Dr. Robert Werrick, who had discovered ʻOumuamua, expressed cautious optimism about the Vega connection. While we can't prove that ʻOumuamua came from Vega, the close encounter provides our best lead for understanding where this object might have originated. It's a tantalizing clue that deserves further investigation. The potential Vega origin also raised questions about the composition and properties of interstellar objects. If ʻOumuamua had formed in the Vega system, its unusual characteristics might reflect the different conditions and processes that shaped planetary formation around a younger, more massive star. This could explain why the object seems so different from anything in our own solar system. The Vega connection also highlighted the interconnected nature of stellar systems within our galaxy. Objects ejected from one star system could travel for millions of years before encountering another system, carrying with them information about the conditions and processes that shaped their formation. The ʻOumuamua represent the first of many interstellar messengers that could provide insights into the diversity of planetary systems throughout the galaxy. Future observations of the Vega system might provide additional clues about ʻOumuamua's possible origin. If astronomers could detect other objects with similar properties in the Vega debris disk, it would strengthen the case for a connection between the mysterious visitor and this iconic star. The story of ʻOumuamua's journey through interstellar space reads like an epic tale of cosmic wandering that spans geological timescales. While the object spent only a few months in our solar system, its true odyssey had lasted roughly 45 million years, a journey that began when dinosaurs still roamed the Earth and ended with humanity's first confirmed encounter with a visitor from another star system. Dr. Corinne Baylor-Jones's detailed trajectory analysis revealed that ʻOumuamua had been traveling through the galaxy at a relatively constant velocity of about 26 kilometers per second relative to the Sun. This speed, while enormous by terrestrial standards, was quite typical for objects moving through interstellar space. Hottenrods and Telbin Telbu Buisel, Offlers and Times so Dire Day Telbu, Arvand and Times and Morn War had been traveling through the galaxy at a relatively constant velocity of about 26 kilometers per second. The Bulbu, the Forge Tasit, Mauther. It suggested that the object had not been dramatically accelerated by any recent gravitational encounters, but had instead been drifting through the cosmic void at a steady pace for tens of millions of years. The scale of this journey was almost impossible to comprehend. During its 45 million year odyssey, ʻOumuamua had traveled a distance of approximately 37 trillion kilometers, roughly 250,000 times the distance from Earth to the Sun. The object had crossed the territories of countless star systems, passed through regions of space with vastly different conditions, and survived encounters with cosmic phenomena that would have tested its structural integrity to the limit. The environmental conditions during this interstellar journey were as alien as anything imaginable. The temperature of interstellar space averages around 2.7 Kelvin, just a few degrees above absolute zero. For 45 million years, the ʻOumuamua had been bathed in this extreme cold, with only the faint warmth of distant stars and the cosmic microwave background radiation to break the absolute chill. Any volatile materials on its surface would have been frozen solid, creating a crust that might have protected the object's interior from the harsh conditions of space. But the cold was only one of the challenges ʻOumuamua faced during its journey. The object had been continuously bombarded by cosmic rays, high-energy particles, traveling at nearly the speed of light that could gradually alter its surface composition and structure. Dr. Aurélie Gilbert-Leparoua from the University of Lyon calculated that over 45 million years, cosmic ray bombardment would have penetrated several meters into the object's surface, creating a processed layer that might explain its unusual spectral properties. The journey had also exposed ʻOumuamua to the subtle but persistent influence of the interstellar medium, the thin gas and dust that fills the space between stars. While this material is incredibly tenuous, with densities millions of times lower than the best vacuum achievable on Earth, its effects could accumulate over such vast timescales. Collisions with interstellar dust grains, though rare, could have gradually eroded the object's surface and contributed to its unusual shape. Perhaps most remarkably, the journey had taken ʻOumuamua through regions of space with dramatically different gravitational environments. The object had passed through the gravitational influences of countless stars, each encounter subtly altering its trajectory. Some of these encounters had been close enough to produce measurable deflections, while others had provided only the gentlest of nudges. The cumulative effect of these gravitational interactions had sculpted the object's path through the galaxy like a cosmic pinball machine. The timing of ʻOumuamua's journey also placed it within the context of our galaxy's dynamic evolution. During the 45 million years of the object's travel, the Milky Way had completed roughly 1/5 of a full rotation. Stars had been born and died, spiral arms had shifted and reformed, and the overall gravitational landscape of the galaxy had subtly changed. ʻOumuamua had been a silent witness to these vast changes, carrying with it information about the conditions and processes that had shaped its long journey. The survival of any object during such an extended journey through interstellar space was itself remarkable. So Denix Sakanina from JPL calculated that the structural stresses from thermal cycling, cosmic ray bombardment, and potential collisions with interstellar debris would have tested the limits of most materials. The fact that ʻOumuamua had arrived in our solar system, apparently intact, suggested that it was composed of relatively durable materials, or had been protected by some form of surface crust. Books. The journey also raised questions about the object's rotation and structural evolution. The complex tumbling motion observed in ʻOumuamua might have been acquired gradually over millions of years, as small asymmetries in the object's shape and composition interacted with various forces during its travel. Alternatively, the tumbling might have been the result of a violent ejection event that had occurred at the very beginning of the journey, preserved across cosmic time like a fossil record of ancient trauma. Dr. Amaya Moromero Martin from the Space Telescope Science Institute used statistical models to explore what ʻOumuamua's journey revealed about the broader population of interstellar objects. Her calculations suggested that the galaxy might contain trillions of similar objects, all following their own lonely paths through the cosmic void. Most of these objects would never encounter a star system, instead wandering through interstellar space for billions of years until they were either destroyed by some catastrophic event or eventually fell into a stellar gravitational well. The 45 million year journey also provided insights into the mechanisms that populate interstellar space with small objects. The fact that ʻOumuamua had survived such an extended journey suggested that the processes that eject objects from planetary systems must be quite efficient. This 45 million year journey also provided insights into the mechanisms that populate interstellar space with small objects. Every star system likely contributes thousands or millions of objects to the interstellar population over the course of its evolution, creating a vast reservoir of wandering bodies that occasionally intersect with other systems. The journey's duration also had profound implications for understanding the object's composition and origin. Any radioactive materials that might have been present when ʻOumuamua began its journey would have decayed long ago, eliminating one potential source of information about its formation. The surface would have been completely altered by space weathering processes, making it difficult to determine what the object had looked like when it first left its parent system. As ʻOumuamua continued its journey away from our solar system, it carried with it the memory of its brief encounter with our star. The object's trajectory had been permanently altered by its passage through the inner solar system, sending it on a new path that would take it to different regions of the galaxy. In perhaps another 45 million years, it might encounter another star system, bringing with it the accumulated history of its cosmic wandering and the faint traces of its encounter with humanity's first interstellar visitor. The discovery of ʻOumuamua fundamentally changed how astronomers viewed our solar system's place in the galaxy. What had once seemed like an isolated cosmic island was suddenly revealed to be part of a vast network of interstellar traffic, with objects regularly passing through our neighborhood from distant star systems. This revelation triggered an immediate and intense effort to find more interstellar visitors, launching what would become one of the most systematic searches in modern astronomy. Dr. Robert Werrick, fresh from his historic discovery of ʻOumuamua, became one of the leading figures in the search for similar objects. Working with the Catalina Sky Survey in Arizona, he began developing new techniques for identifying interstellar objects among the thousands of asteroids and comets discovered each year. The challenge was immense. Interstellar objects would appear briefly, move rapidly across the sky, and show orbital characteristics that were subtly but definitively different from solar system bodies. The search effort was complicated by the fact that interstellar objects were expected to be relatively rare. Statistical models suggested that only one or two such objects might pass through the inner solar system each year, and they would be visible for only a few months before disappearing forever. This meant that survey telescopes would need to scan enormous areas of sky continuously, processing vast amounts of data to identify the few genuine interstellar visitors among the millions of normal solar system objects. The Asteroid Terrestrial Impact Last Alert System ATLAS in Hawaii became another crucial player in the search. Dr. Larry Deno and his team modified their asteroid hunting algorithms to specifically look for objects with hyperbolic trajectories, the telltale signature of interstellar origin. The system's ability to survey the entire visible sky every few days made it ideally suited for catching fast-moving interstellar objects during their brief visits. The European Space Agency's Space Situational Awareness Program, led by Dr. Marco Michele, developed sophisticated trajectory analysis tools that could quickly distinguish between objects with slightly elliptical orbits and those with truly hyperbolic trajectories. These tools became essential for confirming interstellar origin, as the difference between a very elongated elliptical orbit and a hyperbolic one could be subtle and require precise measurements. The search also benefited from advances in artificial intelligence and machine learning. Dr. Mario Jurich, from the University of Washington, developed automated systems that could process telescope data in real time, flagging objects with unusual motion patterns for immediate follow-up observations. These systems could analyze thousands of potential targets simultaneously, dramatically increasing the efficiency of the search effort. The first major breakthrough came when astronomers realized that some objects previously classified as long-period comets might actually be interstellar in origin. Quanzi Yi, from the University of Maryland, began systematically reanalyzing the orbits of unusual comets discovered over the past decade, looking for cases where improved orbital calculations might reveal interstellar trajectories. This retroactive search had the potential to identify interstellar objects that had been misclassified when they were first discovered. Quanzi Yi, from the University of Maryland, began systematically reanalyzing the orbits of unusual comets discovered over the past decade, looking for cases where improved orbital calculations might reveal interstellar trajectories. The theoretical framework for the search was provided by Dr. Avi Loeb and his colleagues at Harvard, who calculated the expected rate of interstellar object encounters based on models of planetary system formation and evolution. Their work suggested that the inner solar system should be visited by one interstellar object every few years, with smaller objects being much more common than large ones. This meant that most interstellar visitors would be too small to detect with current telescopes, making the discovery of objects like ʻOumuamua somewhat fortunate. The search effort also revealed the importance of rapid response capabilities. Interstellar objects typically have very short observation windows, sometimes only a few weeks between discovery and becoming too faint to study. This meant that the astronomical community needed to develop new protocols for quickly mobilizing telescopes around the world to study these rare visitors before they disappeared. Dr. Alan Fitzsimmons from Queen's University Belfast led efforts to establish an international network of observers who could provide rapid follow-up observations of potential interstellar objects. This network included both professional astronomers and advanced amateur observers, who could contribute valuable data during the crucial early phases of object characterization. The search for ʻOumuamua's siblings also highlighted the need for new types of telescopes and survey systems. The upcoming Vera Rubin Observatory, with its unprecedented combination of large mirror size and wide field of view, was expected to revolutionize the detection of interstellar objects. The observatory's ability to survey the entire southern sky every few days would likely increase the discovery rate of interstellar visitors by orders of magnitude. The implications of finding more interstellar objects extended far beyond simple discovery. Each new object would provide additional data points for understanding the population of small bodies in interstellar space, the efficiency of ejection processes in planetary systems, and the physical properties of materials that could survive million-year journeys through the cosmic void. The search effort also raised questions about how to prioritize observations of multiple interstellar objects. If several such objects were discovered simultaneously, the astronomical community would need to develop strategies for allocating telescope time and resources to maximize the scientific return from these brief encounters. As the search for ʻOumuamua's siblings continued, it became clear that humanity was entering a new era of astronomy, one in which our solar system was recognized as part of a dynamic, interconnected galactic environment where objects regularly moved between star systems, carrying with them information about the diversity and evolution of planetary systems throughout the galaxy. On August 30th, 2019, amateur astronomer Gennady Borisov was conducting his routine observations from his private observatory in Crimea when he spotted something extraordinary. Using a 0.65-meter telescope he had built himself, Borisov detected a fuzzy object moving across the sky with unusual speed and trajectory. Within days, his discovery would prove to be humanity's second confirmed interstellar visitor, and it would be completely different from ʻOumuamua. The object, initially designated T/2019 Q4 and later renamed 2I/Borisov in honor of its discoverer, immediately stood out from ʻOumuamua in almost every way. Where ʻOumuamua had been mysterious and enigmatic, 2I/Borisov was reassuringly familiar. Ogobas. It displayed a clear coma and tail, the classic signatures of a comet, and its behavior matched what astronomers expected from a typical icy body heated by the sun. Dr. Piotr Guzik from Jagiellonian University in Poland led one of the first detailed studies of 2I/Borisov's composition. His spectroscopic observations revealed clear evidence of water vapor, carbon monoxide, and other molecules commonly found in comets from our own solar system. Finally, Guzik remarked, "We have an interstellar visitor that behaves like the objects we're familiar with. It's a comet, plain and simple." The stark contrast between 2I/Borisov and ʻOumuamua was immediately apparent to astronomers. While ʻOumuamua had shown no signs of outgassing, despite its close approach to the Sun, 2I/Borisov began displaying clear comet-like activity when it was still well beyond the orbit of Jupiter. This behavior was exactly what scientists expected from an icy object being heated by solar radiation. Dr. Alan Fitzsimmons from Queen's University Belfast, who had been one of the leading observers of ʻOumuamua, noted the dramatic difference. 2I/Borisov is behaving exactly like a comet should. It has a nucleus, a coma, and a tail. It's outgassing in ways that we can detect and measure. In many ways, it's more similar to comets in our solar system than ʻOumuamua was to any object we've ever seen. The nucleus of 2I/Borisov was estimated to be roughly 1 kilometer in diameter, making it significantly larger than ʻOumuamua's estimated size. The comet's activity level was comparable to what would be expected from a similar-sized comet from our own outer solar system, suggesting that 2I/Borisov had formed under conditions similar to those that created the Kuiper Belt objects and Oort cloud comets in our own system. One of the most significant findings was that 2I/Borisov's gas production rates and composition were remarkably similar to those of solar system comets.
Dr.
Martin Cordner from NASA's Goddard Space Flight Center used radio telescopes to detect hydrogen cyanide (HCN) in the comet's coma, finding concentrations that matched those in typical solar system comets. This suggested that the basic chemistry of comet formation might be universal regardless of which star system the objects originated from. The trajectory analysis of 2I/Borisov provided additional insights into its origin. Unlike ʻOumuamua, whose path was difficult to trace backward with certainty, 2I/Borisov's trajectory could be more precisely determined. The calculations suggested that the comet had originated from the general direction of the constellation Cassiopeia, though identifying its specific parent star system remained challenging. Dr. Ye Kwanzi from the University of Maryland used the comet's orbital characteristics to estimate that it had been traveling through interstellar space for millions of years before entering our solar system. Like ʻOumuamua, 2I/Borisov had endured an epic journey through the cosmic void, but its icy composition had been preserved by the extreme cold of interstellar space. The discovery of 2I/Borisov also provided crucial statistical information about the population of interstellar objects. The fact that 2 such objects had been discovered within 2 years suggested that interstellar visitors might be more common than initially thought. This had important implications for planning future observations and understanding the efficiency of ejection processes in planetary systems. Perhaps most importantly, 2I/Borisov served as a crucial comparison point for understanding ʻOumuamua. The fact that the second interstellar visitor behaved like a normal comet made ʻOumuamua's unusual properties even more remarkable. It suggested that while some interstellar objects might be similar to bodies in our solar system, others might represent entirely different classes of objects with properties we had never encountered before. The discovery of 2I/Borisov proved that ʻOumuamua was not just a unique curiosity, but part of a diverse population of interstellar objects with widely varying properties and behaviors. High on a mountaintop in the Chilean Andes, construction crews are putting the finishing touches on what will become the most powerful survey telescope ever built. The Vera Rubin Observatory, named after the astronomer who provided crucial evidence for dark matter, represents a revolutionary leap in our ability to detect and study interstellar objects. When it begins operations, this technological marvel will likely discover more interstellar visitors in its first year than humanity has found in all of previous history. The observatory's primary instrument, the Legacy Survey of Space and Time (LSST), will photograph the entire southern sky every few nights with unprecedented depth and precision. Jelko Ivesic, from the University of Washington, who leads the LSST project, explains the revolutionary nature of this capability. We'll be creating a movie of the entire visible universe, capturing every change, every new object, every unusual motion. For interstellar object detection, this represents a quantum leap in our capabilities. The telescope's specifications read like science fiction made real. Its 8.4-meter primary mirror will collect light from celestial objects, while a 3.2 billion pixel camera, the largest digital camera ever built, will capture images covering an area of sky equivalent to 40 full moons simultaneously. Each image will be so detailed that it could resolve objects as small as a golf ball from a distance of 15 kilometers. But the true power of the Vera Rubin Observatory lies not just in its hardware, but in its systematic approach to sky surveillance. The telescope will revisit the same regions of sky multiple times each night, allowing astronomers to detect objects that move, change brightness, or appear and disappear. This capability is perfectly suited for identifying interstellar objects, which typically reveal themselves through their unusual motion patterns. Dr. Mario Juric, also from the University of Washington, leads the development of the sophisticated software systems that will process the observatory's data stream in real time. His team has created algorithms that can identify potential interstellar objects within hours of their detection, automatically flagging them for immediate follow-up observations. We're essentially creating an early warning system for interstellar visitors. Jurich explains. The goal is to catch these objects as early as possible, when they're still far enough away to study in detail. The impact on interstellar object discovery is expected to be dramatic. Current estimates suggest that the Vera Rubin Observatory will detect one interstellar object every month, compared to the current rate of roughly one every few years. This 100-fold increase in detection rate will provide astronomers with the statistical sample size needed to understand the true diversity and properties of interstellar objects. The early detection capability will also solve one of the major problems that plagued the study of ʻOumuamua: insufficient observation time. By detecting interstellar objects months or even years before they reach their closest approach to the Sun, the observatory will provide astronomers with extended windows for detailed study. This will allow for comprehensive spectroscopic analysis, precise trajectory determination, and potentially even spacecraft missions to intercept these visitors. Dr. Lynn Jones from the University of Washington has been developing specialized algorithms for identifying interstellar objects among the millions of solar system bodies that the observatory will catalog. Her work focuses on the subtle orbital characteristics that distinguish interstellar visitors from ordinary asteroids and comets. The challenge is that interstellar objects are rare needles in a haystack of millions of solar system objects, she notes. We need automated systems that can reliably identify these rare visitors without being overwhelmed by false positives. The observatory's impact extends beyond simple discovery to detailed characterization of interstellar objects. The high-quality imaging will allow astronomers to study the rotation periods, brightness variations, and color properties of these visitors with unprecedented precision. This detailed characterization will be crucial for understanding their composition, structure, and origin. The Vera Rubin Observatory will also enable new types of studies that were impossible with previous telescopes. For the first time, astronomers will be able to study the statistical properties of interstellar objects in detail, determining their size distribution, composition range, and origin patterns. This statistical approach will provide insights into the efficiency of ejection processes in planetary systems and the physical conditions in interstellar space. The observatory's southern hemisphere location provides excellent coverage of the galactic plane, where interstellar objects are most likely to be found. This positioning will complement northern hemisphere surveys, providing global coverage of the sky and maximizing the chances of detecting interstellar visitors regardless of their approach direction. Dr. Robert Werrick, who discovered ʻOumuamua, is excited about the observatory's potential. The Vera Rubin Observatory will revolutionize our understanding of interstellar objects. We'll go from studying individual curiosities to understanding entire populations of these visitors. It's going to transform interstellar object research from a field based on rare discoveries to one based on comprehensive surveys. The observatory is also expected to discover interstellar objects that are too faint or too distant to be detected by current telescopes. This will extend our detection capabilities to smaller objects and longer distances, providing a more complete picture of the interstellar object population. Some of these newly discovered objects might show properties even more unusual than ʻOumuamua, further expanding our understanding of what's possible in the universe. As the Vera Rubin Observatory prepares to begin its systematic survey of the sky, it represents humanity's most ambitious attempt to understand our place in the galactic neighborhood. The observatory will transform our solar system from a place of occasional surprise visits to a well-monitored crossroads where we can study the diverse population of objects that travel between the stars. After years of intense scientific investigation, debate, and analysis, the astronomical community has reached a tentative consensus about ʻOumuamua, though consensus might be too strong a word for the collection of carefully hedged conclusions that represent the current state of scientific understanding. What emerges from the extensive research is a picture of an object that was probably natural in origin, likely composed of materials similar to those found in our solar system, but possessing characteristics that pushed the boundaries of what we considered normal for celestial bodies. The most widely accepted explanation for ʻOumuamua's mysterious acceleration centers on subtle outgassing of hydrogen or other light gases that were below the detection threshold of our instruments. Dr. Darrell Seligman's hydrogen iceberg theory, while controversial, has gained grudging acceptance among some researchers as the most plausible explanation for the object's behavior. The idea that ʻOumuamua could have been composed largely of hydrogen ice, continuously sublimating as it approached the Sun, explains both the acceleration and the lack of visible outgassing. However, this explanation comes with significant caveats. The hydrogen iceberg theory requires conditions for formation and survival that seem extreme even by astronomical standards. For such an object to exist, it would need to have formed in an environment cold enough to freeze hydrogen, likely in the outer regions of a planetary system, and then survive millions of years of interstellar travel without completely sublimating away. Many scientists remain skeptical that such conditions are plausible. An alternative explanation that has gained support involves more conventional outgassing of water vapor or other molecules, but at levels so low that they were undetectable by existing instruments. Marco Michele's refined trajectory analysis suggests that even minimal outgassing, perhaps producing only 10 circumflex 8 of the mass loss seen in typical comets, could account for the observed acceleration. This explanation has the advantage of requiring only conventional materials and processes, though it still leaves questions about why such minimal outgassing would occur. The scientific community has largely reached consensus on ʻOumuamua's basic physical properties, though significant uncertainties remain. The object was probably between 100 and 400 meters in its longest dimension, with an extreme elongation ratio of at least 6 and possibly as high as 10. Its surface was likely covered with a reddish layer of organic compounds that had been altered by millions of years of cosmic ray exposure, giving it spectral properties unlike anything in our solar system. The tumbling rotation, with a period of 7.3 hours, is now understood to be the result of either collision damage during the object's interstellar journey or asymmetric forces during its ejection from its parent star system. The complex rotation state provides strong evidence that ʻOumuamua was a coherent solid object rather than a loose collection of debris, though its exact internal structure remains unknown. Regarding its origin, the consensus points toward ejection from another planetary system during the chaotic early phases of planet formation. The object's velocity and trajectory are consistent with gravitational ejection by a giant planet, similar to the processes that populated our own Kuiper Belt and Oort cloud. The potential connection to the Vega system remains speculative, but represents the best available lead for understanding the object's specific origin. The density question remains one of the most contentious aspects of the consensus. Estimates range from as low as 0.1 grams per cubic centimeter, suggesting a highly porous or hollow structure, to as high as 2-3 grams per cubic centimeter, indicating a solid, rocky composition. This uncertainty affects virtually every other aspect of ʻOumuamua's characterization and reflects the fundamental difficulty of studying such objects with current technology. The scientific community has definitively rejected the most exotic explanations for ʻOumuamua's properties. The artificial origin hypothesis, while mathematically consistent with the observations, is considered highly unlikely, given the availability of plausible natural explanations. The extreme requirements for an artificial light sail to survive interstellar travel, combined with the philosophical principle of favoring natural explanations, have led most astronomers to dismiss the extraterrestrial technology hypothesis. The tria, wrfdirasmo suridiniuris parv, se neutral. However, the consensus acknowledges that ʻOumuamua represented something genuinely new in our experience of celestial objects. Dr. Alan Fitzsimmons, who was involved in many of the early observations, summarized the current understanding. ʻOumuamua was probably a natural object, but it was unlike anything we'd seen before. It forced us to expand our conception of what's possible in the universe. The consensus also recognizes that many fundamental questions about ʻOumuamua remain unanswered and may never be resolved. The object's brief visit and rapid departure meant that crucial observations were never made, and its current distance makes further study impossible with existing technology. This has led to a certain humility in the scientific community about the limits of our understanding. The investigation of ʻOumuamua has also revealed the importance of rapid response capabilities for future interstellar visitors. The consensus emphasizes that the scientific community was unprepared for such a discovery, and that new protocols and technologies will be needed to maximize the scientific return from similar objects in the future. Perhaps most importantly, the consensus recognizes that ʻOumuamua was likely representative of a much larger population of interstellar objects. The statistical models suggest that such objects regularly pass through our solar system, and the discovery of 2I/Borisov has confirmed that interstellar visitors show a wide range of properties and behaviors. ʻOumuamua may have been unusual, but it was not unique. Despite years of intensive study and countless research papers, ʻOumuamua departed our solar system, carrying with it a host of fundamental questions that continue to perplex scientists and fuel ongoing research. These lingering mysteries represent more than just gaps in our knowledge. They point to deeper questions about the nature of interstellar objects, the processes that create them, and the limits of our current understanding of the universe. The most persistent mystery remains the exact mechanism behind ʻOumuamua's acceleration. While the scientific community has largely accepted that some form of outgassing was responsible, the specific process remains unclear. If the object was indeed a hydrogen iceberg, how did it survive millions of years of interstellar travel? If it was outgassing conventional materials like water vapor, why were these emissions completely invisible to our most sensitive instruments? The acceleration was real and measurable, but its cause remains frustratingly elusive. The question of ʻOumuamua's internal structure continues to puzzle researchers. Was it a solid monolithic object, or did it have a more complex internal architecture? The extreme elongation and tumbling motion suggest either a highly unusual formation process or subsequent modification during its journey through space.
Dr.
Zdeněk Šekanina's models indicate that the object might have been a fragment of a larger body. But if so, what kind of catastrophic event could have created such a distinctively shaped piece? The composition mystery runs even deeper than initially apparent. Hall spectroscopic observations provided some clues about the surface materials. They revealed virtually nothing about the object's interior. The reddish surface coloration could have been a thin veneer created by space weathering, masking entirely different materials underneath. Without direct sampling or more detailed observations, the true composition of ʻOumuamua may remain forever unknown. The origin question, while partially addressed through trajectory analysis, still lacks definitive answers. The potential connection to the Vega system is intriguing, but unprovable with current data. Even if ʻOumuamua did originate from that system, we still don't know the specific processes that created and ejected it. Was it formed during planet formation, or was it created by some later catastrophic event? The trajectory calculations can tell us where the object might have come from, but not how it came to be. The density and mass of ʻOumuamua remain among the most fundamental unsolved puzzles. These basic physical properties affect virtually every aspect of the object's behavior and evolution, yet they could not be determined from the available observations. The uncertainty in these values propagates through all theoretical models, making it difficult to distinguish between competing explanations for the object's properties. Dine Dufa, Metri and Sealine Dent of ʻOumuamua remain among the most fundamental unsolved puzzles. The question of ʻOumuamua's representativeness looms large in current research. Was this object typical of interstellar visitors, or was it a rare anomaly? The discovery of 2I/Borisov, which behaved like a conventional comet, suggests that interstellar objects may show a wide range of properties. This raises questions about the diversity of conditions in other planetary systems and the variety of processes that can create interstellar objects. The survival mechanisms that allowed ʻOumuamua to endure its interstellar journey remain poorly understood. The object had been traveling through space for millions of years, subjected to cosmic ray bombardment, thermal cycling, and potential collisions with interstellar debris. How did it maintain its structural integrity over such timescales? What protective mechanisms or material properties allowed it to survive when similar objects might have been destroyed? The timing of ʻOumuamua's discovery also raises unanswered questions. Why was this the first interstellar object detected, when statistical models suggest that such objects should pass through our solar system regularly? Were previous visitors missed due to observational limitations? Or was there something special about ʻOumuamua's trajectory or properties that made it easier to detect? The detection capabilities and observational strategies developed for studying ʻOumuamua revealed significant gaps in our preparedness for future interstellar visitors. The rapid discovery to characterization timeline left many important observations incomplete or impossible. Future interstellar objects will undoubtedly present their own unique challenges, and the ʻOumuamua experience has highlighted the need for better detection systems and response protocols. Perhaps most fundamentally, ʻOumuamua raised questions about the nature of scientific explanation itself. When an object exhibits properties that don't fit neatly into existing categories, how do we decide between expanding our theories to accommodate new phenomena and invoking more exotic explanations? The debate over ʻOumuamua reversion reflected deeper philosophical questions about the methodology of science and the criteria for accepting extraordinary claims. These unanswered questions ensure that ʻOumuamua's scientific legacy will continue long after the object itself has disappeared into the darkness of interstellar space. Each mystery represents a potential breakthrough waiting to be unlocked by future discoveries, better theories, or more sophisticated observational techniques. The brief visit of ʻOumuamua to our solar system may have lasted only a few months, but its impact on our understanding of the universe will endure for generations. This small, mysterious object fundamentally altered humanity's perception of our place in the cosmos, revealed the dynamic nature of our galactic neighborhood, and opened new frontiers in astronomy that continue to reshape how we study the universe. The most immediate impact was the realization that our solar system is not an isolated island in space, but rather a busy intersection in a vast network of interstellar traffic. Dr. Avi Loeb captured this paradigm shift perfectly. ʻOumuamua taught us that we live in a cosmic metropolis, with visitors from other star systems passing through our neighborhood regularly. We're not alone in the universe. We're part of a vibrant, interconnected galactic community. This revelation has profound implications for our understanding of planetary system formation and evolution. The discovery that objects regularly move between star systems means that planetary systems are not closed loops, but open systems that exchange materials throughout their lifetimes. Rocky planets, gas giants, and small bodies can all be influenced by visitors from other systems, potentially affecting their evolution in ways we had never considered. The implications extend to astrobiology and the search for life beyond Earth. If objects like ʻOumuamua regularly traverse interstellar space, they could potentially carry biological materials between star systems. This concept, known as panspermia, suggests that life might not need to arise independently in each planetary system, but could spread throughout the galaxy via interstellar objects. While no evidence of biological materials was found in ʻOumuamua, the possibility remains intriguing for future interstellar visitors. This concept, known as panspermia, suggests that life might not need to arise independently in each planetary system, but could spread throughout the galaxy via interstellar objects. The discovery also revolutionized our understanding of the interstellar medium, the space between stars. Previously thought to be nearly empty, we now know that this region contains vast numbers of objects ranging from dust grains to kilometer-sized bodies. Dr. Amaya Moro-Martin's statistical analyses suggest that the total mass of interstellar objects might be comparable to the mass of all the stars in the galaxy, making them a significant component of the universe's structure. ʻOumuamua's mysterious properties forced astronomers to confront the limitations of their theoretical models and observational techniques. The object's extreme elongation, unusual acceleration, and lack of visible outgassing challenged fundamental assumptions about how small bodies behave in space. This has led to the development of new theoretical frameworks and observational strategies that will benefit the study of all small solar system bodies. The controversy surrounding ʻOumuamua's origin also highlighted important questions about the methodology of science itself. The debate over whether to consider artificial explanations for the object's properties reflected deeper philosophical questions about how scientists should approach anomalous phenomena. Alan Fitzsimmons noted that ʻOumuamua forced us to examine our own biases and assumptions about what constitutes legitimate scientific inquiry. The discovery has also had practical implications for planetary defense efforts. If interstellar objects regularly pass through our solar system, they represent a new category of potential threats that must be considered in any comprehensive planetary defense strategy. While ʻOumuamua posed no danger to Earth, future interstellar visitors might follow trajectories that could bring them closer to our planet. The technological legacy of ʻOumuamua is equally significant. The efforts to study the object led to advances in automated detection systems, rapid response protocols, and data analysis techniques that will benefit many areas of astronomy. The upcoming Vera Rubin Observatory incorporates many lessons learned from the ʻOumuamua experience, and its enhanced capabilities will likely revolutionize the study of transient astronomical phenomena. The discovery also demonstrated the importance of international cooperation in astronomy. The study of ʻOumuamua involved telescopes and researchers from around the world working together to maximize the scientific return from the object's brief visit. This collaborative approach has become a model for how the astronomical community responds to rare and time-sensitive discoveries. ʻOumuamua's impact on public engagement with science has been equally profound. The object's mysterious properties captured the public imagination in ways that few astronomical discoveries have achieved. The possibility that it might be artificial technology from another civilization sparked widespread interest in astronomy and space exploration, inspiring a new generation of scientists and engineers. The discovery also highlighted the importance of citizen science and amateur astronomy. Gennady Borisov's discovery of 2I/Borisov using a homemade telescope demonstrated that important contributions to astronomy can come from unexpected sources. This has led to increased support for amateur astronomy programs and citizen science initiatives. The philosophical implications of ʻOumuamua's visit extend beyond science to questions about humanity's place in the universe. The object served as a tangible reminder that we are part of something much larger than our solar system, a vast galactic ecosystem where matter, energy, and potentially life itself move freely between star systems. This perspective has influenced discussions about space exploration, planetary stewardship, and our responsibilities as a spacefaring species. The discovery also underscored the importance of preserving dark skies and supporting astronomical research. ʻOumuamua was detected only because of sophisticated ground-based telescopes operating under clear, dark skies. The increasing threat of light pollution and space debris could hamper our ability to detect future interstellar visitors, making the preservation of astronomical observing conditions a matter of cosmic importance. Looking toward the future, ʻOumuamua has established a new field of study within astronomy. Interstellar object research is now a recognized specialty, with dedicated conferences, journals, and research programs. The object's visit has also influenced the design of future space missions, with several proposals for intercepting interstellar objects before they leave our solar system. The discovery has also inspired new theoretical work on galaxy formation and evolution. If interstellar objects are as common as ʻOumuamua's discovery suggests, they might play important roles in distributing heavy elements throughout the galaxy and influencing the chemical evolution of planetary systems. This could affect our understanding of how the universe evolved from its primordial state to its current complex structure. Perhaps most importantly, ʻOumuamua reminded us that the universe is far stranger and more dynamic than we had imagined. The object's brief visit opened our eyes to new possibilities and challenged us to think beyond the boundaries of our current knowledge. In doing so, It fulfilled one of the most important functions of scientific discovery. It showed us that there is still so much we don't know, and that the universe continues to hold surprises that can fundamentally change our understanding of reality. So there you have it, ʻOumuamua's story, from its sudden appearance in our cosmic neighborhood to its mysterious departure back into the darkness. We followed the breadcrumbs, we analyzed the data, we debated the possibilities. What did we learn? That our solar system isn't the quiet, isolated place we once thought, but visitors from distant star systems pass through our neighborhood regularly. That the universe is far stranger and more connected than we ever imagined. ʻOumuamua forced us to expand our understanding of what's possible. It challenged our assumptions. It showed us that even with our most sophisticated instruments and theories, the cosmos can still surprise us. But perhaps most importantly, it reminded us that we're part of something much larger, whole. We're not alone on a lonely planet orbiting a lonely star. We're part of a vast galactic community where matter, energy, and maybe even life itself moves freely between worlds. The mystery of ʻOumuamua will continue. Future interstellar visitors will bring new puzzles, new revelations, new reminders that the universe is far more dynamic and interconnected than we ever dared imagine. In the end, ʻOumuamua didn't just visit our solar system, it opened our eyes to the true nature of our cosmic neighborhood. What aspect of ʻOumuamua's mystery fascinated you most? Was it the impossible acceleration, the extreme shape, or the possibility that we might have encountered something truly alien? Share your thoughts in the comments below. If this journey through space's greatest mystery sparked your curiosity, hit that like button and subscribe for more explorations of the universe's most puzzling phenomena. Your support helps us continue bringing you these deep dives into the cosmos. Ready for another mind-bending space mystery? Check out our next video or the playlist on the screen.